process control is application of control system. Suppose you want to control the room temperature. Suppose you want to control the room temperature means, suppose say you want to control at 24 degrees centigrade, you want to control. It means, what is the first thing we have to do? First thing we have to do what? Let us assume that a cooling system is available. Let us assume that a cooling system is available. That will make this room cool. What is the first thing? I want to maintain at 25 degrees centigrade. What I have to do? First thing? Measure the room temperature. The first thing is we have to measure the room temperature. So we should measure the temperature and then you have to compare this with what value you want to maintain. You want to maintain at 25 degrees centigrade. That is called set point, new term. So most of the terms will be new. That's why set point. So you want to maintain at 25 degrees centigrade means that 25 degrees centigrade is called the set point. This present temperature may be 30 degrees centigrade. That is called process variable, PV, process variable. We have to find the difference between set point and process variable. Set point and process variable. That is called error. You will get error if you subtract the process variable from set point. If you subtract the process variable from set point, you will get error. If error is there, then only we have to control. Suppose 24 minus 30 means minus 6 degrees centigrade. The difference is 6 degrees centigrade. That is minus. It means the temperature is higher than the required one. That's why we have to turn on the cooling system. So to turn on the cooling system, we need a controller. You need a controller to turn on the cooling system. It will on or off. If the difference is, if the temperature is above 24, it will turn on. Below equal to 24, it will turn off. So what will happen? Initially, it is at 30 degrees centigrade. You want to maintain at 24 degrees centigrade. This is time. So it will decrease because it is compared. It is initially it is 6 degree centigrade. That's why it is compared. That's why this controller turn on the cooling system. That's why the temperature is decreasing. Am I correct or not? Time also elapses. X-axis is time axis. Y is actual temperature. This 24 is set point. This is PV. This is process variable. Process variable starts decreasing. But this controller will turn on if the error is negative. The error is negative, then only it will turn on. Let us assume like that. So when just it crosses 24, say 23.9, the actual temperature becomes 24 means equal 0. If it becomes negative, then only it will turn off. Yes. So it decreases. It starts decreasing. When set point equal 24 means the cross variable also comes to 24, then error becomes 0. Suppose the temperature falls below 23.9 means error becomes positive. That's why it is turned off. The cooling system is turned off. What will happen to the temperature of process variable? What will happen to the process variable? That is room temperature. Now it is 23.9. Now it is 23.9. The cooling system is turned off. What will happen to the room temperature? It will start increasing. Any other answer? Any other answer? Here, cooling system is here. The cooling system means it circulates the air. Am I correct or not? Inside some element is at below 24 degrees centigrade, maybe ice temperature or less than ice temperature, negative temperature. In that, the room air is going there and give away its temperature and comes. It is circulating. What is the element temperature now? Inside element. Some element is there inside that is cooled less than 25 degrees centigrade. Obviously, this air is going there and give away its heat and coming at low temperature. That's why the room temperature is decreasing. Now tell me the answer. What will happen to the room temperature? Hereafter, it is now cooling system is turned off. What will happen? What happens to room temperature? I am asking. Now 23.9. I will put the question this way. Is there any further decrease or not? Here in the cooling system, this is the cooling system, let us assume. Here some element is there. Let it be. That is mechanical system. We need not bother about it. This is cooled down by some circulating system. The room temperature, room is here. Room is here. This air is going in and a fan is there. That's why it is blowing out its air. Which air it is blowing? Room air is again blown out there. It means it sucks the room air and blows out. So the room air is falling on this. It gives away its heat and coming down, again coming out. That's why temperature is decreased from 30 degree to 23.9. Now the cooling system is off. Why off? Error becomes positive. Error becomes positive. That's why that controller turned off cooling system. Now tell me whether any further decrease in temperature or not. Huh? Till that element also reaches the room temperature, it will be less than room temperature. That's why there will be a further decrease in temperature. Further decrease in temperature. As he said, till it reaches room temperature. This element reaches this element. This element reaches room temperature. Till then there will be a decrease in temperature. So there is a further decrease in temperature. But after some time, as he said, the room temperature and here inside that cooling element also same temperature. Till then it decreases. Then it starts increasing. Am I correct or not? Whenever it just crosses 24, what will happen again? The cooling system again turned on. Cooling system again turned on. Am I correct or not? Now what you can expect? Is there any further increase in temperature or immediately it starts decreasing? There will be a further increase in temperature because you cannot expect immediately. Two reasons. One is, as he said, the element temperature is not immediately coming to low temperature. It takes some time. That is one reason. Another reason is the sensor is here. Cooling air is coming here. So it has to circulate this much distance. Till then the room will get heat from all sides. From all sides it is getting heat. But from only one place it is getting cool air. Are you able to understand? That's why there will be a further increase in temperature. But after some time, because of the cooling element, starts decreasing. As earlier I said, it happens like this. It oscillates around set point. Are you able to follow? It never becomes 24. It never becomes 24. It oscillates around set. This type of controller is called on-off controller. On-off controller. This type of controller is called on-off controller. Do you understand this? On-off control. If you put the on-off controller, always it will oscillate around set point, never settles at set point. What is our aim? What is our aim? We want to settle at 24, but it never settles. On-off controller never settles at, have you seen anywhere that on-off controller? Where? Huh? Refrigerator, AC, where? Any other place? Only on, off. But it never reaches that, whatever the temperature we mentioned, never reach. Maybe less than that or above. Accidentally, it may be equal. Accidentally, it may be equal. And you cannot expect an entire room in the same temperature. That is also there. What is our temperature? 37 degrees centigrade. That's why whatever we excel is at 37 degrees centigrade. Excel is 37 degrees centigrade. That is also there. Okay. Anyhow, if you put an on-off controller, it will not work out. It will not work out. That's why we can convert this controller into a proportional controller. Proportional. Proportional controller means the output is not 100%. Here, the output is 100%. 100% means that this element will get maximum cooling. Say -5 degrees centigrade. Let us assume what is that? -5 degrees centigrade. Its temperature, this cooling element, this blue color, cooling element becomes -5 degrees centigrade. -5 degrees centigrade. Let us assume. But what is the set point? 24 degrees centigrade. We can cool this room by keeping this cooling element less than 24. But if it is -5 means quickly comes to 24. Suppose it is 0 means it takes long time to come 24. If it is 5 degree means it will take further time. If it is 10 degree means it will take further time. If it is 15 degree means it will take further time. So time will increase to reach the 24. Anyhow, if cooling element is less than 24 means definitely it will reach 24. So instead of keeping -5, let us assume that I am keeping from 5 to -5. 5 to -5. I can vary 5 to -5 or 10 to -10. What is there in assumption? Let us assume like that. 10 to -10. Or I can assume 22 because I have to convert it to 24 only. 22, 0. Let us assume what is that? Its temperature can be varied from 20 to 0. So I will make this element equal to 0 if the error is more. Large error means suppose initially it is 30 degrees centigrade. I have to bring to 24. Large error, 6 degrees centigrade. That's why I'll make it 0. It is very close to 24. Then I will make it 20. So small difference. Small difference. That's why there won't be this much difference. There won't be any this much difference. The difference will be like this. It comes to 24 and the difference will be very small, because by the time I made the cooling element equal to 20. You understand that? Depends upon the error. If the error is very small, I will keep 20 degrees centigrade. If the error is very large, I will keep 0 degrees centigrade. So in between all values will come. Suppose if it is the error is 3 degrees centigrade, what is the middle value? 10 degree I will keep. I understand this point. That is called proportional controller. So error varies from 6 degrees centigrade, 6 degrees centigrade to 0 degrees centigrade. 0 degrees centigrade. Error -6 degree to 0. Because when it is 30 degree, error is -6. When it is error is the 24 degree means error is 0. Here, this varies from 0 degree centigrade. If error is 6 degree, minus 60 degree means I will make 0 degree centigrade to 20 degree centigrade. Because I have to keep 25 degree centigrade. Am I correct? This type of variation is called proportional controller. Because the controller output is proportional to error. Proportional to error. What is the controller gain? Error is 6 degree. The change in cooling element temperature is 20 degree. 20 divided by 6, how much? 3 point something. 3.66. Am I correct or not? 3.66. So, if error is 1 degree means the temperature will be 3.66 degree less than this. Less than the 24 degree centigrade. If 6 degree means its temperature will be 0. Because 6 multiplied by 3.66 equal to 20. Proportionally, it is varying. It is proportionally varying. The cooling element temperature is varying from 0 to 20 degrees centigrade. That is called proportional control. Here, large oscillation I noticed. That's why I changed it to proportional controller. Actually, I am taking theory because I cannot tell the lab directly. Because you do not know what is PID controller. I have to tell some, I have to tell very short theory. Then only I can explain the experimental setup. That's why I'm telling all these things. So oscillation reduced, but you cannot make set point equal to PV again. Again, you cannot make set point equal to PV. If you use proportional only. That's why here the controller is changed to proportional only, P only. That is called, depends upon the error, cooling element temperature will be there. That is called a proportional controller. That's why I'm putting P. I removed that on-off controller. I removed that on-off controller. I put a proportional controller. Still then you cannot make 24. You cannot make 24. Because how the controller works, controller output equal to, what is the controller output? M, controller output is named by M. M equal to 0 to 20 degrees centigrade. Am I correct or not? Controller output is 0 to 20 degrees centigrade. When it will give 0, 30 degree centigrade. Room temperature is 30 degree, it will give 0. If the room temperature is 24, it gives 20 degrees centigrade. Am I correct or not? Suppose the error is 0. What is the controller output? Error is 0. What is the controller output? Off only. Completely turned off. Because controller output is 0. Again, it will not make because the controller output is function of error. Error is required to make the controller work. Are you able to follow what I am saying? To make the controller work, you need error. That's why you cannot make error equal to 0. That's why you cannot make error equal to 0. That's why proportional controller also fails. To some extent, it will work. But anyhow, some error will be there that you will study in theory. Always there will be error. Here it is 30 degrees centigrade. Here set point is 24 degrees centigrade. If you put the P only controller, it will come and it will oscillate, then it will settle like this. It will settle. Some error will be there. Say 1 degree centigrade. 1 degree centigrade error will be there. It will settle at 25 degrees centigrade. Let us assume 25 degrees centigrade. It never comes to 24. It never comes to 24 because to make functional that P controller, it needs error. That's why it will make 25 only. It never makes 24. Not 25. For example, I am telling 25. There is a calculation is there. At that temperature, it will maintain. But never 24. So P controller also failed. That's why you need some other controller. How to understand that controller? Let us assume that I am driving a car. I am driving a car. Or let us assume that I am driving a car. I want to drive the car at 60 kilometers per hour. I want to drive the car at 60 kilometers per hour. I am giving correct acceleration. Let it be bike or car. I am giving correct acceleration. What is the speed now? 60 kilometers per hour. What is set point? 60 kilometers. It is in my mind. Am I correct or not? Set point is in my mind. 60 kilometers per hour. Car speed also 60 kilometers per hour. What is the error? 0. Error is 0. Suddenly, some road slope is there. What will happen? I am not changing the accelerator. Road is slope, positive slope. What will happen to the speed? Decrease. So what I have to do? I have to increase the acceleration. Am I correct or not? I am increasing. Road slope is still same. I am increasing the accelerator. Again, the speed decreased to 54. Now again it comes to 60. Am I correct or not? Now, road again becomes horizontal. What will happen to the speed? Increase above 60. Another example. Road is horizontal only. I am giving correct acceleration. Suddenly the wind is against the car. What will happen to the speed? Decreases. I am giving additional acceleration. What is the speed? Again 60 kilometers. Again 60 kilometers. Wind is still there. I am giving additional input. Now it is 60 kilometers. What is the additional acceleration given? How much? How to calculate? Mathematically, what is that value? Mathematically, you tell something. How I calculated that additional input? It is proportional to what? I am putting the question in another way. It is proportional to what? That is correct. Which speed? Which speed? My additional acceleration proportional to what? How much it is reduced? It reduced from 60 to 54. I gave additional input based on error 6. 60 minus 54, 6. For that, I gave additional input. Now, what is the error? 0. Error is 0. Still, I am giving additional input. Are you able to follow what I am saying? Still, I am giving additional input. That's why it is keeping at 6 kilometers. That's why this error is proportional to what? Now, the question is, this error is proportional to what? Which error? Now error is 0. This additional input is proportional to what? Now the error is 0. Always the additional input is depends upon error only, not speed. The difference between set point and PV only. The additional input is proportional to what? Old error. It is proportional to old error. So we need a device that will give output depends upon old error. We need a device that will give output proportional to old error, not present error. The proportional controller gives output depends upon present error. That's why for a proportional controller, you need a present error. This controller output is about past error. There is no error now, but earlier there was an error. Earlier there was an error. If you plot that error, how it looks like, how it is looking like, the set point is 60 kilometers per hour. That is set point. The speed is, let us assume, speed is decreased to 54 kilometers per hour. It is decreased. Why? Because of wind. But the controller takes necessary action. That's why it goes up. Again, it goes to 60 and remains at 60. Mathematically, what is the controller output from this graph? What is the additional controller output from this graph? That is proportional. I am putting the error plot here. Initially error up to this point, 0. It goes up to 60 kilometers per hour. I am plotting for error, positive error. This is negative error. So 60 minus 54 positive. That's why it starts increasing this way. This is error plot. This is error plot. This is speed plot. This is speed plot. In the error plot, in the error plot, it increases. I take necessary action. That's why it comes down to 0. Error comes to down to 0. But a little bit oscillation, after that it is settled. From this error plot, can it tell the additional control output proportional to what? From this graph, can it tell? What is this graph? Error graph. Am I correct or not? Because of wind, it deviated and the controller takes necessary action. That's why it comes to 60 kilometers per hour. Sir, not 60 degrees centigrade, 60 kilometers per hour. It came to again to 60 kilometers per hour. Set point. Can you tell the additional controller output proportional to what? I'll tell. Proportional to this area. Proportional to this area. After that, any area is there? No, it is integrated. If you add all this area and calculate, that much input has to be given to the additional input has to be given. That's why the error becomes 0. Once the error becomes 0, is there any area? No area. Till error becomes 0, the area has to be added together. Area has to be added together. That is called integration. If you do integration, suppose this is error graph means, if you integrate that error, you will get area under this graph you will get. If you integrate, what you will get? Yeah, area under the graph you will get. Integration means that is the meaning. You can find, if you integrate any graph, suppose I am having a graph like this. If you integrate this, let it be sine theta. Theta varies from 0 to 180 degree. If you integrate sine theta, d theta, you will get error under this graph. If you integrate up to 360, you will get 0. Why? This is positive, this is negative, getting cancelled. That's why if you integrate sine theta, you will get 0. In mathematics, that's why if you integrate sine theta, that's why you are getting 0. If you integrate up to 180 degree, you get some value. That's why here positive area is higher, negative area is less. That's why you will get some value. What you have to integrate? You have to integrate the error. You have to integrate the error. So this P mode will not remove the error. That's why I'm including one more mode that is called I mode, integral mode. P plus I controller I am going to use. P plus I controller I am going to use. Both mode will be there. P mode will work only when error is there. To speed up the response, P mode is required, not to remove error. P mode never remove error, but I mode will remove the error. So PI controller has to be used. Now we will come to, that's all about PI. D mode is there, that we rarely we use. In your experiment, you won't use. Anyhow, I'll tell one more mode is called, that's why it is called PID controller. D mode is to speed up the response. Speed up the response. D mode means derivative. This is integral mode, I. D mode means derivative. Integral of E dt means you will get error under the graph. dE by dt will give what? Derivative. What it will give? Physical meaning. What is the physical meaning of dE by dt? What is that? Is called what? Speed, velocity. Velocity. At what speed the error increases? If the error increases very fast, the controller will give more output. If it decreases very fast, it will give more controller output. If no change, dE by dt is 0 means horizontal. Once it is settled at set point, it will be horizontal. No controller output. No need, because it is not changing. Whenever it changes, then only it will work. We won't use. We will use only for slow process. You will study those things later. If I take those things, it will be a theory class. So we have to use a PID controller to control the process, but we will use only P or only P plus I only we will use in the lab. We won't use D mode now. D mode will be used only in thermal process. We are not going to do any experiment on thermal process. That's why we will use P mode or P1, P plus I mode. I understand this. Now we will come to laboratory experiment. The laboratory experiment, the first experiment is modeling and tuning of level process. level process. Process means a system. In process control, we used to call it as process because it is the marriage between chemical engineer and instrumentation engineer. Instrumentation engineer, no control. Chemical engineer, no process. He knows the process. Suppose a factory manufacturing fertilizer. He knows the process only. He do not know control. They are studying process control. That is different. But it is not their major subject. Major subject is for you. Control. So they know process. What will happen if the pressure increases? What accident may happen if the pressure increases? They know. But they do not know about control. You know. Level process. Level process means in industries there will be units called first unit, second unit. The first unit will give its output to the second unit. First unit produce something. First unit produce something that is given as input to the second unit. It may be a pharmaceutical industry. It may be a pharmaceutical industry to prepare tonic or some other thing. Or it may be a fertilizer industry. Or it may be a energy production, NLC, Neyveli Lignite Corporation that produce power, Everything comes under process control. All control comes under process control. There, the first unit gives output to the second unit. Its flow rate. Flow rate means it gives some liquid. Say it gives 10 liters per hour it gives. Let us assume. If it gives 10 liters per hour as feed to this second unit, then only the finished product is its output will be good. Quality. You can market it. The quality is not good, you cannot market. So it should be maintained at 10 liters per hour. But this unit, there will be changes. Already we have seen, we want to drive the car at 60 kilometers per hour. But can we control the wind speed? Can we control the slope of the road? We cannot control. That's why we have to adjust something in the car, not outside. Outside we cannot control. Like that, this 10 liters per hour may be varied because of some other parameters that we cannot control. That's why if any changes in 10 liters per hour, then there will be a quality will be degraded in the second unit. So how to maintain 10 liters per hour? For that, what we can do is, this is the first unit that produce approximately 10 liters per hour. Sometimes it may be 11 liters per hour, sometimes it may be 9 liters per hour. I understand this. So what we can do is, this first unit output is given to a level process. This is a level process. Level process. It is given to the level process. Here, I can put one controller here that will maintain 10 liters per hour. 10 liters per hour. Then it is called a flow process. I understand this. This is called flow process, not level process. The flow rate, 10 liters per hour is flow rate, not flow. Flow rate is controlled. That way they can control. Or they can control. Another way is they can keep the level constant. They can keep the level constant. From here, it is coming from here. They can adjust the inflow rate. They can adjust the inflow rate so that the level will be constant. The level is constant. The outflow rate will be constant. You can notice at your home, if the tank is full, you will get the maximum flow rate in your tap at home. The tank is almost empty means you will get less flow rate. So depends upon the level, you will get the flow rate. Depends upon the level, you will get the flow rate. The level is, if you maintain the level constant, the flow rate here will be constant. Am I correct or not? We are maintaining the level. So instead of controlling the flow rate, we can control the level. If you control the level in the middle tank, this is first unit. Here it is second unit. This is second unit. The middle unit is level process. It will maintain the level. That's all. Whatever coming from the first unit received by here, and it will adjust the level so that the outflow rate will be constant. not large variation. It is average out the changes. It average. Suppose there is a sudden change from 10 liters per hour to 13 liters per hour means if you put a level control, it will be gradually phased out, averaged out. Small change, 10.1, 10.2, like that it increases, and 13 sudden increase will be averaged out. So this level process is used to average out the sudden changes. Have you understand that? That's why we have to study about the level process. The first process you are going to study is level process. Level process is nothing but a tank. In that we have to maintain the level. We have to maintain the level. How we can maintain the level? To maintain the level, there will be a valve. This valve means, this is called valve. New term. Valve means like a tap at your home. You can adjust the opening. There at home, our hand will be used to adjust the opening. Here it will be a pneumatic signal will be used. Pressure signal will be used to open and close. The valve will be used 3 to 15 psi. PSI will be used. 3 to 15 PSI will be used to adjust the valve opening. How valve works, we will see in some other experiment. So, by adjusting this valve opening, 0 to 100%, you can vary the flow rate from 0 to 10 liters per hour. Let us assume 10 liters per hour. You can adjust, let us assume. So, by adjusting the valve opening, the liquid is coming from somewhere, constant flow rate, but if we adjust the valve opening, flow rate will change so that level can be maintained constant. You understand that? Here I want to maintain the level constant because it is a level process. Suppose I want to maintain the level, means what should be measured? I want to maintain level constant. What should be measured? Oh, not opening of the valve. I want to maintain level constant. What should be mentioned? What is the process variable? What is the process variable? Level is the process variable. What is the level is the process variable. Say this tank level. Level means height. Level means height. Height of this level is say 5 feet. Total tank level is 10 feet. I want to maintain 50% of that level. So 5 feet level has to be maintained. So what is the process variable? Liquid level, liquid height. Level you couldn't understand. That's why. Liquid height is called level. Level has to be measured. Level has to be measured. How to measure level? For that, a DPT is there. Sensor is DPT. Differential pressure transmitter. DPT is there. Differential pressure transmitter. It is available in the lab. DPT means its output will be 4 to 20 milliamps. Its output will be 4 to 20 milliamps. Current how much varies? 4 to 20 milliamps. If the tank is empty, it gives 4 milliamps. The tank is full, it gives 20 milliamps. It gives 20 milliamps. So this DPT means differential pressure transmitter. One end is connected to the bottom of the tank. Other end is open to atmosphere. This end is open to atmosphere. This end is connected to bottom of the tank. The tank level varies, pressure applied to the DP transmitter is varying. A pressure sensor, DP transmitter is what? A pressure sensor. The pressure sensor output is depends upon the pressure applied at one end. What is the pressure at the top of the tank? Atmospheric pressure. So the pressure between the two can be, you can draw level transmitter like this also. It means what? Top atmospheric pressure, bottom tank pressure. That's why it gives output proportional to level, proportional to height. So we can call it as a level transmitter. Here for level transmitter, you are using DPT as a level transmitter. DPT as a level transmitter. So that 4 to 20 milliamps is error signal. we have to generate error signal. That's why this 420 milliamps is given to 420 milliamps is given to controller. Given to the controller. For controller, we are giving set point. Set point equal to, we are giving 5 feet. Set point is given. We cannot give in terms of 5 feet. Here, what is we are getting? 4 to 20 milliamps. How we can subtract 5 feet from 4 to 20 milliamps? You cannot measure because the unit is different. So we have to give set point in terms of 4 to 20 milliamps, or this 4 to 20 milliamps will be read by the controller in terms of percentage, 0 to 100%. It will read like that. If 4 milliamps means 0% level, 20 milliamps means 100% level. Have you understand that? Controller will read the 4 to 20 milliamps like that. Controller will read the 4 to 20 milliamps like that. Have you understand this point? 4 to 20 milliamps will be read as 0 to 100%. Let us assume that if we give 100% input to the valve will be fully opened. If we give 0%, that is 3 psi to the controller, valve will be fully closed. Let us assume. If we give 15 psi, valve will be fully opened. If we give 3 psi, valve will be fully closed. So valve opening can be varied by adjusting 3 to 15 psi. That is given by the controller. The controller output also depends upon the error 4 to 20 milliamps. The controller is P plus I controller. P plus I controller. How P plus I controller works already we have discussed. P plus I controller works based on error. Here I am giving, instead of 5 feet, I am giving 50%. Set point is given as 50%. It means total level is 0 to 10 feet means 50% means 5 feet. So set point is 50%. Actual level is measured by DPT and it is given here. That is also 50% means what is error? 0. If it is not 50% means error is there. Based on that, the controller will give 4 to 20 milliamps. The controller will give 4 to 20 milliamps. That 4 to 20 milliamps is converted into 3 to 15 psi pressure signal. I to P, sorry. This will convert I to P. I to P converter convert that 420 milliamps into 3 to 15 psi. That 3 to 15 psi is connected to this valve. This is the experimental setup. In this, you have to do experiment. Now I will explain. You may get confusion so far. Once again, I am going to tell. This is the complete diagram. If you listen at least now, you can understand. We have to control the level. Say level at 50%. Total level is 100%. You forget about feet and all. Total level is 100%. I want to control at 50%. That's why I am giving set point equal to 50% to the controller. The actual level is measured by DPT. That is, whatever the actual level will be given to the controller. The difference between the two is getting as error. That error signal we are getting in terms of 4 to 20 milliamps. Controller gives 420 milliamps. That is given to I to P. Because this 420 milliamps will not work in the level valve. Valve we need pressure signal to adjust it to opening. That's why this 4 milliamps corresponds to 3 psi. 20 milliamps corresponds to 15 psi pressure. That signal is given to the valve. So valve opening will be adjusted. How we are adjusting the accelerator in the car, accelerator in the bike, like that, it will adjust the valve opening. The controller output will adjust the valve opening. So that level will be maintained at 50%. Now again, we'll come to this example. We want to control the level. That's why level is measured by DP transmitter. The DPT gives its actual level in terms of 4 to 20 milliamps. If the tank is empty, it gives 4 milliamps. The tank is full, it gives 20 milliamps. It means it gives 0 to 100%. That is read by the controller. You want to maintain at 50%. This 50% is compared with the actual level. Depends upon the error, it will give controller output, say 4 to 20 milliamps. depends upon that, the valve will be opened. Now we'll come to this. The level is 50%. Initially, the level is 50%. Am I correct or not? Set point is 50%. What is the error? 0. 0 means 4 milliamps. 0 means 4 milliamps. I to P gives how much? 3 psi. Valve will be closed. Valve will be closed. So the level starts draining. But what is the input required? What is the input required? In the level process, I didn't put the outflow rate. Always there will be outflow rate to the next second process. One valve that gives flow rate to the next level, next process. You understand this point? I forgot to put this outflow rate. This is output. Then only you need adjustment. This outflow rate is proportional to level. This outflow rate is proportional to level. That's why you need a controller. Depends upon the level, the flow rate will come. The outflow rate is Q output equal to some constant times level. Square root of H. Depends upon H, the outflow rate will be there. That is given to the second process. That is there. So I want to control the level at 50%. I am measuring the actual level that gives in terms of 4 to 20 milliamps. The controller read in terms of percentage. The set point is given as 50%. Both are 50%. That's why controller output is 4 milliamps. That's why I to P is 3 psi. Therefore, valve is closed. What should be the valve opening to maintain at 50%? Partially opened. Am I correct or not? 50%. Valve should be opened at 50%. The valve always should be open at 50%. If level decreases, it will open 55%. The level increases, it will open 45%. That's why always it should open 50%. Am I correct or not? Valve always should be at 50% opening. Then only level will be maintained at 50%. That's why that additional input the controller has to give, that is called a bias. That is called a bias. The controller output is equal to the M equal to what is the PI controller? It is based on error. Controller gain multiplied by error. Am I correct or not? Controller gain is called Kc. Kc multiplied by error. This is proportional controller. What is the integral controller? Kc by Ti is a constant. Integral of E dt. Am I correct or not? This is the controller output. If error is 0 means, if error equal to 0 means, control output is 0. That's why this will not work out. Therefore, valve will completely closed. To avoid that, we have to add something that is called a bias. Bias is always 50%. 4 to 20 milliamps means what is the middle value? 12 milliamps. 12 milliamps always, the controller output always must be 12 milliamps. 3 to 15 psi means always 9 psi must be there. If you want to drive the car at 60 kilometers per hour, if your set point equal to PV, that means you want to ride at 60 kilometers per hour. Actual speed is 60 kilometers. Are you closing the accelerator? No wind, no slope, horizontal. Road is horizontal, no wind. The speed is 60 kilometers per hour. Set point is 60 kilometers per hour. Speed is 60 kilometers per hour. What is the error? 0. Are you giving some acceleration or not? You are giving some acceleration to maintain 60 degree. That is called a bias. In controller also should give some bias so that it should be maintained at 50%. That bias is 50%. So that will not comes under calculation. How it comes, we will see later. How it comes, we will see later. How to calculate that, we will see later. But here, what is tuning we have to see? What is tuning we have to see? Here I put some constant Kc multiplied by error. Here I put Kc by Ti, integral of E of t I put. These constants varies depends upon the process. Depends upon the process. For that, I will give one example. Today, I am driving a old car. Same slope while going from here to Marakanam, same slope. Some speed is changing. That's why I'm giving additional acceleration. So speed is maintained at 60. Tomorrow, I am going to drive a new car. Whether I have to give same additional input or different? Different. So it varies from process to process. That's why this Kc by T, Kc, Ti, these constant we have to calculate depends upon the process. That is called tuning. That is called tuning. We have to, depends upon the process, we have to find Kc, Ti. Kc, Ti we have to find. That values we have to enter correctly. Then only the, can I drive new car like old car or old car like new car? I cannot drive. I have to drive as if it is there. I understand this. So depends upon the process, I have to calculate this KCTI. That is called tuning. What is simulation? I did any simulation. What is simulation? What is simulation? Huh? You did any simulation anywhere? Where? Oh, VLC did simulation. Simulation means without doing experiment, find the result. Without doing experiment, finding the result is called simulation. How to find the result without doing experiment? Physical experiments you are not doing, but you want the result. That is called simulation. If you want to do the experiment without if you want the result without doing experiments, we need the mathematical equation. That is called the model of the system. If you know mathematically how to represent the system, then you can find the result mathematically. So mathematically find the result is called simulation, not computer. Using computer is not simulation. Inside computer, what we are using? Mathematical equations. So solving the mathematical equation is called simulation. Okay, anyhow, it is not important now. Here also, to find Kc and Ti, you need the mathematical model of this process. Finding that mathematical model of the process is called modeling. What is time constant? I think in transducer lab, you might have find the time constant of RTD. You find that RTD. You inject the RTD inside the boiling water. At what time it reaches 63.2% of final value. Time taken for that, and you will find the time constant. Am I correct or not? That experiment I did. Oh. If time constant large mean, what is the meaning? Time constant large mean, what is the meaning? Time constant small means, what is the meaning? Why time constant is important? Why time constant is important? Time constant is large means it takes long time, slow device. Time constant is very small means it quickly reaches the final value. Small time constant. Have you understand this? So time constant is important. Suppose I'm having a process. You can take that RTD example. Room temperature is 30 degrees centigrade. The boiling water is at 100 degrees centigrade. If you inject the RTD into the boiling water, what will happen? Temperature will increase like this. Am I correct or not? It goes to 100 degrees centigrade. Time taken to 63. What is the time? This is the time constant of the RTD. This is the time constant of the RTD. X-axis is time. Another RTD, it goes like this. Which is faster? If you see the time constant of the blue one, it will be lesser. Another RTD, it goes like this. If you take the same 63.2%, how much? Larger. So if the device is slow, time constant is large.
new car means small time constant. Old car means large time constant. That's why handling the car is very easy. So depends upon the time constant, these Kc and Ti we have to find. The formula for Kc equal to Tp, time constant of the process, divided by gain of the process, Kp, and dead time of the process, Td. We have to find these three parameters called modeling of the process. You are modeling in the transducer lab. You are modeling the RTD in the transducer lab. You are finding, you can write the model of the transducer equal to gain equal to 1 for all measurements, because for 100 degree it gives 100 degree. That's why K equal to 1. Ts plus 1. Like that you wrote the model. Am I correct or not? For RTD you wrote like this. This T only you found in the experiment. Am I correct or not? So this Tp is the time constant of this level process. This Kp is gain. If I open 50%, what is the level inside? If I open 100%, if I change the level, 5% while opening is changed. What is the change in level? That is called Kp. Kp equal to change in level divided by change in valve opening. Change in level divided by change in valve opening. Valve opening, we won't talk in terms of 3 to 15 psi, not in terms of 4 to 20 milliamp. We'll talk in terms of percentage. Suppose I am increasing 5% valve opening. Level also changes 5%. What is the gain? 5% divided by 5%. 1% per percent. Gain equal to 1% per percent. So if I open, level is changed 5%, valve opening is 5%, that is equal to 1% per percent. Therefore, gain of the process is 1% per percent. Suppose the level is changing 10%. Level is changing 10%. Valve is opened only 5%. What is the gain of the process? 2% per percent. If we change the valve opening some percentage, level also changes in terms of percent. Everything should be in percentage only. So that Kp you can find in terms of percentage. Tp you know how to find. Already you did the experiment in the lab. You know how to find. This Td only you do not know how to find. The Td is dead time in the process. Some process, if we change the input, it won't change immediately. It takes some time to respond. For example, in the level process, I changed the valve opening. Say 5%. I changed the valve opening 5%. But there is no appreciable increase for some time. After that, it starts increasing. Then it settled at new value, say 10%. Earlier, it is 50%. Now it is changed to 60%. What is the change in level? 10%. But initially, there is no change in level. That part is called dead time. That is called dead time. New term, dead time of the process. Sometimes that may happen in some process. If you give some input, it won't change. It takes, after some time only it will respond. After some time only it responds. That is called dead time. What is the time constant? Time taken to reach 60%, 50 to 60, that is 10% change. 63.2% of 10%. 6.32. 6.32% to change 6.32%. What is the time taken? This only. This part is the TP, not total. After that time, what is the time taken to reach 63.2%? That is TP. What is KP? KP is for 10% change, how much you gave? Valve change. 5% opening. That 2% per percent is valve opening change. So you know KP, you know TP, you know TD. Now you can calculate KP. KP equal to, already I told you that for a PI controller, it is 0.9 times TP divided by TD KP. This is the formula. This is the formula, that's all. Thumb rule. 0.9 times TP divided by TD KP. KP is gain, you know how to calculate. TP is time constant, you know how to calculate. Dead time is There is no response for some time. After changing the valve opening, you change it to 5%, but there is no appreciable increase in level. That is called dead time. If you calculate all these three, you can find KP. KC, controller gain. KC equal to 0.9 times TP divided by TD KP. KP is what? Here change is 10%. For how much change in valve? 5% change, that is equal to 2% per percent. That is KP. TP is say 5 seconds or 50 seconds. TD is 5 seconds. Therefore, KC equal to 50 divided by 5 multiplied by 2. That's all. We can find KP. KC, controller gain. You can find KC. We have to find TI. Already one in the PID controller, KC already we found. We have to find TI. We have to find TI. Integral time. That is called integral time. TI equal to 3.33 times TD. That's all. Thumb rule. Now you know all parameters. This process is called tuning. Tuning the controller. Finding TP, TD, KP is called modeling. Because if you know all this, I can write the transfer function. G of S equal to, what is TP? TPS plus 1. I can write like this. Numerator, I have to put KP. Where I have to write TD? Dead time can be written like this. TDS. We have to write like this. This is the mathematical model of the process. That's why it is called modeling of the process. From the model, we are taking TP, KP, TD. If you put all these values in the tuning rule, you will get KC. TI also you can put T. If you substitute TD, you will get TI. That's all. Tuning is over. So we modeled, we tuned. Now we can control closed loop. How to do closed loop control? That what we have to do is, we'll come to the experiment now. I'll hereafter I explained all technical points so far. Now I will explain you how to do the experiment. How to do the experiment. You are provided with the level process. You are provided with the level process. There will be a TP transmitter. DPT is there. DPT is there. That will give 4 to 20 milliamps. 4 to 20 milliamps. This DPT is called two-wire transmitter. This DPT is called a two-wire transmitter. Two-wire transmitter means four-wire transmitter. Have you studied? Two-wire transmitter? Have you studied industrial instrumentation? Yes, but you didn't study that two-wire, four-wire transmitter. Any instrument, if asked, it has to work means what is required? It has to work. The DP transmitter has to work. For that, what is required? Huh? Power supply. Very good. You need power supply. 24-volt power supply is required. It will give 4 to 20 milliamps. So how many wires required? For 4 to 20 milliamps, 2 wire. For power supply, 2 wire. 4 wires required. That's why it is called 4-wire transmitter. But if you connect all these together in series, then it is called 2-wire transmitter. But whatever, in most of the industries, they will use only 2-wire transmitter, not 4-wire transmitter. They will connect DPT plus terminal is connected here. DPT has negative terminal also. They will connect to 24-volt power supply. This is 24-volt power supply. This is negative terminal is connected to negative terminal. 24-volt power supply. This is 24-volt power supply. Here I want to drop this in how much? 250 ohm resistor. That is the load. That's all. The load, this is the experimental setup in the lab. 24-volt power supply, DP transmitter and 250 ohm all are connected in series. How many wires are used here? Only 2 wire. Power supply, load, this is load. This 420 milliamps has to be given at 250 ohm. Why? If you give across 250 ohm, for 20 milliampere, what is the drop across 250 ohm? 20 milliamps multiplied by 250, how much? 5 volt. You will get 5 volt. 4 milliamps multiplied by 250, how much? 1 volt. So it gives 1 volt means tank is empty. 5 volt means tank is full. That is given to the PID controller. PID controller receives 1 to 5 volt. Have you understand this? This is called two-wire transmitter. Two-wire transmitter. Power supply, DPT and 250 ohm all are connected in series. All are connected in series. Have you understand this? 3 and 5. PID controllers pin number 3 and 5. This 250 ohm is connected. Across 1, 2. PID controller works on 230 volt. Pin number 1 and 2, you will get 230 volt. That's why you don't think it is electronic instrument. The back panel you should not touch. That's why I'm telling this. You are giving how much? 230 volt power supply. Inside it is converted into 24 volt or 12 volt or 5 volt. I understand that. That's why back panel, how much power supply we are giving? 230 volt. It is open, not like electronics lab. Electronics lab enga venalum kai veppinga. புரியுதா? நீங்க வந்து ஓபனா இருக்கும். You should be very careful. So 230 volt power supply, single phase 50 hertz power supply is given to that PID controller. Here we are giving 0 to 100% level. 0 to 100% level is given as input. PV is given here. That PID controller has pin number 3, 5. You are giving that process variable. Set point you can adjust inside. That display will come. You can adjust the set point. Set point is given as 50%. So the controller output is coming here. That is going to be given to I to P. Here it is giving 4 to 20 milliamps. This I to P will give 3 to 15 psi. For that I to P require 20 psi pressure. 20 psi. That is also given. 20 psi pressure signal is given. Here the DPT works under 24 volt power supply. That's why it is given. This is mechanical device. That's why it requires 20 psi. If we give 4 to 20 milliamps, it gives 3 to 15 psi. Power is 20 psi. Mechanical power is given. That 3 to 15 psi is connected to this valve. Connected to this valve. This valve 3 to 15 psi. This valve will adjust the flow rate here. That's why level will be maintained at 50%. How to do the experiment? This is the experimental setup, actual experimental setup. If I put, initially if I draw the same drawing, you cannot understand. That's why now I drawn the detailed experiment. From where the water is coming, this outflow rate is going to some sump. This is the experimental setup. How to do experiment, you will see now. The experiment consists of 3 parts. One is modeling. We have to find what and all? Kp, Tp, Td. That is called modeling. Second is tuning. We have to substitute these values in the formula. You will get tuning rule, tuning parameters. Third part is closed loop control. Always you want to control at 50%. Always you want to control at 50% or 35% or 30%. Depends the wherever you will be asked to control, there you have to maintain the level. Let us assume that always I want to control at 50%. First bring the process to 50%. Suppose you want to drive the car at 60 kilometers per hour, means first thing what you will do, you bring the car to 60 kilometers per hour. Then only you can maintain. Maintenance only controller will do. Controller cannot bring to 50%. We have to bring to 50%. The controller will maintain at 50%. So now you bring the process to 50%. That's why what we have to do, in the bias we have to give. For that, we have to put the controller in 2 modes. One is called manual mode. Another one is called auto mode. You have to put the controller in manual mode. If you put the controller in manual mode, means it is not closed loop. It is called open loop. Open loop means what is the controller output? M equal to what I wrote? Kc multiplied by error plus Kc by Ti integral of E dt plus bias. I said, this part will not work in manual mode. This part will not work. Automatically it calculates the controller output. That automatic controller output will not work. Then it is called manual mode. In manual mode, if you put M, manual mode, there are some, you can change from manual to auto to manual. Initially, you put the controller in manual mode. First step I told. First step is take down. Step one is put the controller in manual mode. Other initial steps they will tell. You have to turn on the setup, you have to turn on the motor, those things they will tell. Put the controller in manual mode. Theoretically, I am speaking. Put the controller in manual mode. Adjust the controller output. Second step, adjust the controller output. Already I told you that you can adjust bias in manual mode. Say controller output equal to 50%. You are adjusting the controller output to, there will be an increase decrease button. You see the diagram? There is an increase decrease button and one escape. Escape and enter. Enter key. Escape key. One increase decrease button. Only 4 buttons are there. In manual mode, if you put one more button is there, that is called an auto manual. If you put the controller in manual mode, you can increase decrease the controller output. You make controller output equal to 50%. You make controller output by increase decrease. You make controller output equal to 50%. Now the level starts increasing from 0. Increase. If the level increases, controller output also increases. Let us assume that this outflow rate is value is open to 50%. The level after sometimes take 20 minutes. After 20 minutes, the level comes to 50%. The outflow rate equal to inflow rate. Outflow rate equal to inflow rate. Say inflow rate is 5 liters per hour. Now outflow rate also equal to 5 liters per hour. What will happen to level? Level remains same. That's all. Now you are not using automatic mode, manual mode. Manually you are adjusting the controller output to 50%. Level remains at 50%. Now check whether level is settled or not. Third point. Check whether the level is settled or not. When it will settle, if inflow rate equal to outflow rate, then only it will settle. How to find whether it is settled or not? There will be a display here. Display will be there. That display will display the PV. The PV will be displayed. Initially, it will be 0%. After some time, it becomes 50% display. PV will be displayed in red. Am I correct? Cross variable will be displayed in red. It varies from controller to control, manufacturer to manufacturer. In our controller, it will be red. That's all. PV will be displayed. Now PV is settled at 50%. How to find whether it is settled or not? It comes from 0 to 50. The last digit only varies. 50.1, 49.9, 50.2, 49.9. Like that it varies. It means it is settled. Then you made it 55%. 55%. Start recording the change in level in my notebook. So far you didn't note any change. It is settled at 50%. Now you give 50 to 55. Start note down. Initially it is at 50%. Then 50.4, 50.0, 50.0. 3-4 readings like that. After that it starts increasing. 50.4, 50.9, 51, 52, 53. Like that, let us assume that it is settled at 60. It increases and settled at 60. How to find whether it is settled or not? The last digit only oscillates. It means settled. So now, first part almost over. First part almost over. The same way it did the experiment in transducer lab, finding time constant of RTD. You plot those values here. You subtract 50%, whatever the value available, plot this response, it will be looking like this. This is called a reaction curve. Reaction curve. You got reaction curve. You got reaction curve. You got reaction. It is between time and level, percentage level. You subtract 50% from that, it varies from 0 to 10%. It varies from 0 to 10% because I subtracted 50. 50 is the nominal value. Note down new term. Nominal level is 50%. Now, always I want to maintain 50%. That's why that is called nominal level. So it varies from 0 to 10%. Find the dead time from the graph. Find the time constant, 63.2%. Time taken, this is called time constant. You got TP, you got TD, you got from the graph. KP you won't get from the graph, but KP equal to what? Change in level, 10%. What is the change in input? 5%. That's why 2% per percent you got. You got TD from the graph, safe. 3 seconds. TP equal to 30 seconds. Just I'm writing some rough value. 3 seconds, 30 seconds, 2%. Therefore, I can find the tuning parameters. Kc equal to 30 divided by TP equal to 3 multiplied by 2. That's all. 10 divided by 2, that is equal to 5. 5 you will get. Kc equal to 5% per percent. Because this is in seconds, this is also in seconds, these two getting cancelled. 2 is percent per percent. If you take inverse, then also it is percent per percent. Therefore, this is percent per percent. You got 5. Am I correct or not? 30 divided by 3, 10 divided by 2, 5. So you got Kc. What is TD, TP, Ti? Ti equal to 3.33 TD. That is equal to 3.33 multiplied by 3 equal to 10 seconds. You got. That's all. Tuning parameters I got. Then transferring from manual to auto mode means that is called the pumpless transfer. Note down this new word. Transferring from manual to auto mode is called pumpless transfer. You simply cannot transfer from manual mode to auto mode. You cannot simply transfer because you initially kept at 50%, then changed it to 55. You got reaction curve. First part is over. Mathematical modeling is done. Then you find the tuning parameters from the mathematical model. Second part is over. Now I have to control. That is the third part, closed loop control. For that, again we made 50% because it takes some time to again settle at 50%. That's why before doing all these calculations, we made that 50% there. Then we will allow to settle at 50%. Now it is settled at 50%. I want to maintain 50% forever. For another 6 months, I want to maintain at 50%. Whether I am there or not, it must be maintained at 50%. You understand this point? Control means that is control. If we put this in closed loop and go away, went home, tomorrow if you come, if you see, it will be at 50% only. That is control. Many changes. If any change in fluctuation, the power supply, the flow rate will change because it is coming from this flow rate is going to sump. From this sump, one motor is pumping from here to here. I'll draw the line. From here to here, from sump, something is some pump is pumping. If any voltage change, what will happen to the pump? Flow rate will change. For that, the controller will take action. It will open more. If flow rate decreases, it will open more. Controller will take necessary action. That is called disturbance. Any disturbance comes because of voltage changes, flow rate will change. But controller takes action. Immediately it will open more. For low voltage, it will give the same flow rate. So that level again it comes to 50. Have you understand this point? That is called control. Even if you come after 1 week, it will be remain at 50%. That is called closed loop control. Now it is in manual mode. It will not control. We only adjusted to 50%. Now we have to put this in closed loop, auto mode. Before changing auto mode, we have to note down some 3 points. First thing is we have to keep the set point correct value. For that, what is the process value here? Where it is settled? 50%. Because controller output is 50%, level is settled at 50%. That's why make set point equal to 50%. Set point equal to 50%. What is the process variable? Process variable also 50%. Now what is the error? 0. First condition is satisfied. Process variable must be at steady state, not 50 transient. Suppose it is going from 55 to 49, let us assume. It goes to 55 to 49 or 60 to 49. In the middle, it will come to 50. No, that time is not steady state. Steady state means it remains at 50. So process variable is remains at 50. It is steady state value is 50. Set point also 50. That condition is first condition, satisfied. Process is at steady state. Set point also equal to process variable. First condition is satisfied. Second condition also satisfied. Process is at steady state. Third condition, controller parameters are entered. How to enter controller parameters? For that, if you press one time escape, don't do auto manual transfer. Press escape when the display is set point. When the display is set point. Here, there should not be O. The display O is not there, means it displays the set point. It must be 50. Why? Process variable is 50. Both are equal. Both are equal. That time you press escape means it will enter inside parameters. It will ask. It will ask for KC. It will ask for KI, TI. Those things madam will explain in the lab. Without controller, I cannot explain those points. You have to enter KC value. You cannot enter KC directly. You have to enter PB there. You have to convert KC into PB. The relation between PB and KC is PB equal to 100 by KC. KC, how much you got? 5. 100 by 5 equal to how much? 20. 20. So 100. So you 100 divided by 5 KC, you calculated 5. In our example, 5. So 100 divided by 5 equal to 20. You have to PB, you have to enter 20. You cannot enter in terms of KC. Some controller available in the market, some controller will work on KC, some will work on PB. This controller works on PB, that's why you have to enter in terms of PB. PB, relation between PB and KC is proportional band equal to 100 by KC or KC equal to 100 by PB. You understand that relation? So we have to enter 20. So we entered 20. We have to enter TI. We have to enter TI. TI equal to 10 seconds. That also entered. That also entered. After that, if we again press escape, it will come out. Escape or enter. After entering these values, we have to press one time enter to accept that value. You have to press enter. After entering 20, you have to press one time enter. It will accept. After that, if you move to the next variable by pressing escape or enter. Escape. Escape, if you enter, press, it will display TI. Enter TI, 10 seconds. You can use increase decrease key to vary the value. 10 and press enter, 10 will be accepted. Then you press escape, it will come out. So you third condition is satisfied. You entered correct tuning parameters. So 3 condition has to be satisfied before transferring from manual mode to auto mode. First condition is process must be at steady state. Steady state means it remains in one value. Steady state, yes, process is at steady state. Set point equal to PV, yes, set point equal to PV. You adjusted the set point. When you can adjust the set point, when it displays set point, you can adjust increase, decrease, set point will be adjusted. If you press enter, set point will be accepted. So you made set point equal to PV, process is at steady state. You entered correct tuning parameters, whatever you calculated. Now process is ready to transfer from manual mode to auto mode. If you press once AM, A/M, auto manual. If you press, the process will be transferred to auto mode. Process will be transferred to auto mode. Now, if any error comes, controller will take action. What is the present process variable? 50. What is the set point? 50. Therefore, no error. That's why it will give 0 plus 50. Already bias is 50. It remains 50. It remains 50. Another 3 hours, let us assume that it is at 50. After 3 hours, let us assume that some voltage is decreasing. Let us assume. What will happen to the flow rate? Will decrease. That's why valve will open more to adjust the flow rate. So that again it will come to 50% level. You understand that? That type of response is called regulatory response. Note down this value. If for any disturbance, the process controller is controlled, controller controls the process, then it is called regulatory response. Instead of 50, you are changing to 60 now. Now you are changing the set point to, after changing to closed loop, you are changing the set point. Now you understand this? Now it is in closed loop. Now it is in closed loop. You are changing the set point to 60. Changing the set point to 55. Let us assume. What is the error now? 5%. The controller will take necessary action to bring the process to 55. After some 20-30 minutes, the level will automatically comes to 55 and remains in 55. This type of response is called servo response. So you have to do two experiments. One is called servo response. Another is called a regulatory response. Regulatory response is for disturbance. Servo response is for set point change. Yes, you have to remember. Set point change. So you change from 50 to 55, the process will settle automatically at 55. You will get the response like this. For PI controller, you will get the response like this. Initially, it is 50%. You change the set point to 55%, you will get the response like this. It remains, this is this new set point. This is old PV, new PV. New PV comes and settled. It will be oscillate like this. The controller cannot directly bring to 55. It will oscillate around and settle at 50. This is called servo response. Servo response. Another regulatory response. We cannot wait till some disturbance in the electricity comes, because we have only 3 hours to do the experiment. That's why we ought to deliberately give some disturbance. How we can give? In that path, one more valve will be there. In that path, one more valve will be there. Hand valve will be there. Like tap in your home. You can adjust that. Deliberately, you close, slightly close. What will happen? Flow rate will decrease. Here, this valve you are closing, this valve will open more. So adjusted. Resistance is adjusted. So flow rate will come again increased. So again it will come to 50. So you are deliberately closing that valve slightly, not much. Slightly if you close, the level starts decreasing, then it increases and comes to 50. Suppose you are doing the experiment here, means what will happen? Because of that valve closed, it comes like this, and again it oscillates and settles. This is called regulatory response. This is second part of third part. Regulatory response. This is servo response. That's all. Experiment is over. We'll see in 5 minutes. I'll explain all these things. Review again. Then we'll finish this class. 3:30. You are having some work. This is the level process. To maintain level. Level is the process variable. Level means height in water height. That is measured by DPT. Differential pressure transmitter. One end of the DPT is connected to bottom of the tank. Other end is open to atmosphere. That's why it gives 420 milliamps. It is given to the controller. Controller reads that 420 milliamps in terms of percentage, 0 to 100%. It gives 0 to 100% controller output in terms of 420 milliamps. That I2P will read that 420 milliamps are 0 to 100%. It gives 3 to 15 psi. That is given to the valve. Valve opening can be adjusted. Depends upon the controller output. This experiment consists of 3 parts. One is modeling, tuning, closed loop control. Closed loop control means we have to transfer from manual mode to auto mode. That process is called bumpless transfer. First, to put the controller in manual mode, give controller output 50%, allow the level to settle. Let us assume that it is settled at 50%. You cannot expect, if you give 50%, you can expect a 50% settlement. You cannot design such process in practical. Theoretically, you can say for 50% open, 50% level, these are all theoretically you can speak.
There, if you give 30%, it may settle at 50%. I understand this. That's why they will tell something, somewhere it is settled. So you cannot expect 50-50 that and all. For conveniently speaking, I am telling all these things, 50-50 and all. Okay. So you gave 50%, it is settled at 50%, let us assume. Now you have to get the reaction curve. For that, once the process is settled at 50%, you change the controller output from 50 to 55%. Once it is, once you change it from 50 to 55, you start noting with respect to periodically you have to note every 3 seconds, every 3 seconds, 5 seconds. Every 5 seconds you note down. Every 5 seconds you note down the values. So in the reaction curve, you have to enter values every 5 seconds. Every 5 seconds in the graph sheet. Every 5 seconds. Or you can draw in the lab software and you can trace as you wish. Graph sheet, or you can trace in Excel, you can put and draw the graph and you can trace in a graph sheet. Trace sheet. In trace sheet you can trace. So you got the reaction curve. From the reaction curve, you know how to obtain TD, dead time. You know how to obtain TP. Time taken from this point. Time taken from this point. Time taken from this point to this point. Here it is dead time is over. Here it reaches 63.2%. That's why this time is TP. KP, you know how to find it. Change in level divided by change in controller output. You got KP, TP, TD. So put in the formula and find the tuning parameters. Kc equal to TP divided by KP. How you are writing the transfer function? G of S equal to, already I told you, KP divided by TP S plus 1. Am I correct or not? E power minus TDS. Whatever in the numerator, KPTD, no, the transfer function. Put everything in the denominator. Whatever in the denominator, you put in the numerator. Formula you can easily remember. So you can remember TP is in the denominator in the transfer function. You put in the numerator. The formula, Kc equal to what? Kc equal to 0.9 times TP divided by Kp multiplied by TD. So you can easily remember the formula. What is Ti? Ti equal to 3.33 times TD, that time. I understand this. So you got the tuning parameters. Second part is over. And did all these things, you got the tuning parameters. Now we have to transfer from manual mode to auto mode. For that, 3 things you have to note down. Whether the process is at steady state. By this time it will be at steady state because you took 20 minutes to calculate. That's why process is at steady state. Now make set point equal to PV. Whatever the PV, you make set point. Now tuning parameter is entered. How to enter tuning parameters? When the display is SP, set point, that time if you press escape, it will ask for Kc and Ti. You can enter those values. If we display manipulated variable, that is O, is there. That time if you press escape, what will happen? It will transfer from manual mode to auto mode, or yes, set point. Display will be changed from set point and manipulated variable. So you have to press auto manual that time. 3 conditions satisfied. Process at steady state, set point equal to PV. You entered the tuning parameters correct values. Now you transfer auto manual. The process will be in auto mode. It means any disturbance comes, controller will take care. Now you have to get 2 responses. One is servo response. Another one is regulatory response. To get servo response, what we have to do? We have to change the set point. We change the set point from 50 to 55. The controller will bring the process to 55. Automatically, in 20 minutes, it will come to 55. That response is called a servo response. Once you change from 50 to 55, note down the values. Whatever the display in the controller, you note down the process variable. So you will get a response like this. This is called a servo response. This is the servo response. This is the servo response. Suppose you are doing the regular response after servo response. Here you give. Here, once it is settled, you give some disturbance. How I told, disturbance is given by adjusting this hand wall. If you adjust the hand wall, disturb. That's why again it will take 20 minutes to settle at that 55%. That response will be looking like this. Initially it is 55. You disturbed it, that's why it come down because you closed the valve slightly. It will, controller will adjust and finally settle at again 55%.
This response is called regulatory response. Second experiment is tuning and closed loop control of flow process. Flow process means it controls the flow rate. In the first experiment, we have seen level process. Level process. In that one control valve is there. The flow rate is adjusted by the pneumatic signal, that is 3 to 15 psi. Pneumatic signal is used for that. I to P is used, and before that one controller is there. This is the controller that gives 4 to 20 milliamps. 4 milliamps means valve is completely closed, zero flow rate. 20 milliamps means fully open, 100% flow rate. In other words, 3 psi means fully closed, 15 psi means completely open. For that, we have to measure the level. A level transmitter is there. Already I have seen a DPT is used to measure the level. And it is compared with the set point. Set point is given to the controller. And the process variable also given to the controller. It finds the difference and gives 420 milliamps according to level. If you consider this part alone, that is called flow process. Here what we are doing, actually to control level, we are controlling the flow rate. In some process, we have to control flow rate. Sometimes we have to control the flow rate. In that case, what is the process? Process will be looking like this. Process will be looking like this. Through this, some flow rate is there. For example, a diesel engine. Diesel engine has to be, the speed has to be controlled irrespective of load. Have you noticed that if load increases, speed will decrease? Have you noticed? Suppose you are cycling. Somebody suddenly sits on the back seat. What will happen to the speed? Speed will decrease. Like that, if you turn on many lamps, the alternator speed will decrease. Alternator speed will decrease. It should not decrease. It should run at the same speed. Why? Because what is the frequency of power supply? 50 hertz. That's why it should rotate at a constant speed. Then only you will get 50 hertz. Otherwise, you won't get 50 hertz. So, irrespective of load, it should rotate in the same speed. That's why a controller is required. So, that will adjust the, suppose the generator is run by diesel, means it will adjust the diesel flow rate. Example I am telling. So, this is such a flow pipe. In that, I want to control the flow rate. To control that flow rate, one valve is there. This valve has to be adjusted to adjust the flow rate. So it has to be measured. It has to be measured. For that, this is orifice plate. You might have studied about orifice plate in the industrial instrumentation. 2 tappings are taken before that orifice plate and after that. And it is given to the DPT, differential pressure transmitter, that gives the flow rate. That flow rate is 4 to 20 milliamps. 100%, 0 to 100% is represented by 420 milliamps by this DPT transmitter. The flow rate we are getting, that should be given to the controller, PID controller. For the controller, we are giving set point also. Set point means what flow rate you require. 50% flow rate is required, I may say. So here also 50% means no problem. Otherwise, the controller will adjust the valve opening. So this is, its output is 4 to 20 milliamps. This 420 milliamps has to be converted into 3 to 15 psi. Again, 3 to 15 psi. That 3 to 15 psi is connected to this valve. So the valve means like tap at your home. In the tap, you have to rotate to adjust the flow rate. Here, we have to give pressure signal that varies from 3 to 15 psi. That the flow rate will vary. The flow rate coming out of this will vary. That's all. This is the flow process. This is conventional flow process. But in the lab, it is slightly different. Here, the problem is here, how the flow rate is adjusted here? The flow rate is adjusted by this valve opening. The valve, if you close, means it increases the resistance. It increases the resistance to flow rate. That's why flow rate decreases. But a pump here always pump the same amount. But because of the resistance, flow rate decreases. It means the pump has to spend same amount of power, irrespective of flow rate. Suppose flow rate is always 50%, means the pump has to spend 100% flow rate power, but it uses only 50%. Power is wasted in the lab, wasted in the valve. It dissipates power. This valve dissipates power. This valve absorbs some power by introducing resistance. That's why there is a large power loss. In a small tap, small power will be wasted. Suppose in the industry, suppose they are using 100 HP motor. 100 HP motor means 8,000 something power, watts. 50% of the power, 50% only you are allowing flow rate, means the 50% of the valve is closed, but the pump can pump 8,000 watts. That much flow rate it can deliver, but only 4,000 watts is used. 4,000 watts is wasted. So nowadays, these are all valves are replaced by variable frequency drive. That we will see now here. Variable frequency drive. So instead of pumping same amount, instead of valve, it is replaced by, this is coming from sump. This is the sump from where we are getting the liquid. This is the sump from where we are getting the liquid. Here we are putting a pump. Let us put like this. This is the pump, or we can put a box shape pump. A box, and it is a pump. This pump speed can be varied. The pump speed can be varied, so that flow rate can be varied from 0 to 100%. Flow rate can be varied from 0 to 100%. Flow rate can be varied 0 to 100% by adjusting the speed of the pump. For that, again, we have to measure the flow rate. A RFI's plate is there. The tappings are taken. A differential pressure transmitter gives 4 to 20 milliamps. That is given to a VFD. That is called VFD. That is given to the 420 milliamps is the cross variable. Actual flow rate is measured. That is cross variable. Set point also given to the controller. This is the controller. That gives again 4 to 20 milliamps. If 20 milliamps it gives, the pump has to run at full speed. 4 milliamps given, pump should be stopped. So its speed varies from 0 to 100%, depends upon this 4 to 20 milliamps. That 4 to 20 milliamps, how to vary the pump speed? How it can be varied? For that pump, one 3-phase motor is there. It is coupled with the pump is just, it will rotate and pump the liquid. That's all. But it should be rotated by a motor. Rotated by a motor. A motor is connected. a three-phase motor is connected. Three-phase motor is connected with that. If the speed of the motor changes, pump flow rate will change. Am I correct or not? So how to change the speed of the motor? Speed of the motor is function of what? N is proportional to three-phase induction motor. Speed is proportional to what? Have you studied the formula in electrical technology? 120 F by P. 120 F by P, where P is the number of poles in the motor, N is the speed of the motor, 120 is constant, F is the frequency of power supply. If you are able to vary the frequency of, but here what we are getting is constant frequency, 50 hertz. That's why if you give that power supply to any motor, the motor speed will be constant. Motor speed will be constant, but we want to vary according to 4 to 20 milliamps. That's why a device called, a power electronic device called VFD, variable frequency drive. To that, this 420 milliamps given, that gives a three-phase power supply. That gives a three-phase power supply to this motor. Its frequency varies from 0 to 60 hertz, 0 to 50 hertz or 60 hertz, depends upon. Let us assume that the motor runs at 60 hertz. So 0 to 60 hertz in UK and Canada's standards are 60 hertz. But Indian and UK standards are 50 hertz. So it's 0 to 60 hertz power supply. It will give constant voltage, but frequency is varying. Its output depends upon 420 milliamps. I will say this way. If 20 milliamps is given 60 hertz, 4 milliamps is given 0 hertz. So frequency varies from 0 to 60 hertz. That VFD will give. That's why the pump speed will be adjusted. This is the experimental setup available in the lab. So the valve is replaced by VFD. This, by using this, we have to adjust the flow rate 0 to 100%. 0 to 100%. I want to do control. For that, here I am using a PID controller. Here I am using a PID controller. PID controller means controller output M equal to what? M equal to Kc multiplied by error plus Kc by Ti integral of E of t dt. That's all. PI controller. Let us use not PID, PI controller. Let us use. PI controller is used. That's why this plus bias. Always bias is required. Already we have discussed why bias is required. Suppose the car is running at 60 kilometers per hour. Are you giving any input, or because of zero error, you are not giving any input? You must give some input to run at 60 kilometers per hour. The same meaning here. If there is no error, means that time it should give something to get the required output. For that, that bias is required. Controller will not find the bias. We have to find the bias. That bias will controller add and it will give. In the previous class, I said if you transfer from manual mode to auto mode, what is happening? What I told you is this formula is implemented in the controller that I told. Before that, what is that? M equal to bias only. Before that, M equal to bias only. It means in manual mode, we are adjusting the bias. Whatever the controller output in manual mode will be included in the auto mode. This is the controller output in auto mode. Auto mode means closed loop. Closed loop. Manual mode is M equal to only bias. Bias is adjusted. Manually, we can adjust the value. But in closed loop, it is constant. Bias is constant. This part becomes constant. You cannot adjust it. If you press up down arrow, you cannot adjust it. Which part adjusts the controller output? This part. This is the variable part. In controller, this is the variable part. This is constant part. In closed loop, in auto mode. In manual mode, this part is 0. This part is 0. This part is 0. No, error is not calculated. Error is not accounted. Always error 0 in manual mode. Error will not be taken into account. Only bias can be adjusted. This is variable in manual mode. So in manual mode, we are adjusting the controller output manually and gives the required controller output so that we will get 50% output. Suppose set point is 50% means we are adjusting in manual mode to get 50% output. 50% output we adjusted. If we transfer from manual mode to auto mode, that you gave something in manual mode, no, that becomes constant there. That becomes constant there. I didn't explain this part in the previous class because I don't want to make you confused. Now you will get some idea. That's why I'm telling now. So what is happening while transferring from manual mode to auto mode? This formula part is included by making bias equal to constant. By making bias equal to constant. That is the function of controller. That is called bumpless transfer. If you do the bumpless transfer means transferring from manual mode to auto mode. If you transfer from manual mode to auto mode, the bias becomes constant and the formula part as function of error is included in the controller output. That's all. Now, what we have to do, tuning means what? We have to find KC, TI we have to find. We have to find KC and TI because it varies from process to process. In the previous class, what we have seen is level process. Its mathematical model is different. Its time constant is very large. Its time constant is very large. But in flow process, time constant is negligible. Like electronic process, time constant is negligible. Here, time constant is in very, very small. So, you cannot use the same KC and TI here. You have to find a different time constant here, different tuning parameters here. You have to find different tuning parameters here based on this process. How to find that? There are two methods are there to find the tuning parameters. Two methods. One is called open loop method. Or this can also be called as reaction curve method. You obtained the reaction curve in the level process. In open loop, you gave 5% change at the nominal level. Nominal level means the level at which you always want to control. That you got a curve, S curve you got. For that open loop change, you will get a curve like this, S curve. It is looking like S, that's why S curve. This curve is called a reaction curve. That's why this method is called open loop method or reaction curve method. So for level process, we will use open loop method or reaction curve method. Another method is closed loop method. Closed loop method or sustained oscillation method. Sustained oscillation method. Sustained oscillation method or closed loop method. This method is reaction curve method. This is applicable for level process because level process is very slow. That's why we are applying open loop method. For fast process only, we can use closed loop method. For slow process, we cannot use. Why we will see now. In control system, you might have studied that. Have you studied root locus? In the root locus, real axis, imaginary axis. If you draw a root locus means, suppose I want to draw a root locus for third order process. Third order process. Third order. This is a third order process. What is the root locus for this? 3 root locus branches. How many branches? 4, 3 poles mean 3 root locus branches. Am I correct or not? One will go to infinity like this. Another one will go like this to infinity. Another one will go like this to infinity. Am I correct or not? This is the root locus. What is root locus? Locus of poles as k varies from 0 to infinity in closed loop. This is third order, you know. S cube plus A S cube plus B S square plus C S plus D. Third order. Am I correct or not? Third order transfer function. Yes, A S cube plus B S square plus E S plus D. I am taking this. Set point is given here. This is cross variable. In control system, you are calling this as reference. This is response or output in control system. Here, this is called set point. This is called cross variable. Okay. Both are same. Here, how you obtained this root locus? Let us assume that for this transfer function, you got this root locus. How you obtained is by varying this k, you plotted the poles. You plotted the poles because this is open loop transfer function. In closed loop, what is the closed loop transfer function? If you write the closed loop transfer function, it will be looking like this: AS cube plus BS square plus CS plus D plus K. Am I correct or not? Denominator, you will get K. That's why you are in the pole is varying pole you got. If you vary K, the denominator poles are moving. That is root locus. If poles are on the right hand side, the system is unstable. So even though you are varying numerator K, the system becomes unstable. The system becomes unstable. When at this point of value, that point is called K max. At K max, it transfers from left hand side to right hand side. Left hand side to right hand side. That's why the system becomes unstable. System becomes unstable. At this point, the system becomes unstable. K max. If K is greater than K max, system becomes unstable. So we should not put any system in the verge of instability. If you put this at this point, the system will always oscillate. The output will be looking like this. I did the experiment on RC phase shift oscillator. How many phase shifts you are introducing? 3 phase shifts, 60, 60, 60. 180-degree phase shift. The amplifier will give 180-degree phase shift. Total phase shift how much? 360. Total gain 1. That's why it always oscillates. Actually, in the lab, what you are doing is you are calculating R value, C value. But either R or C will be fixed. You will calculate either C or R. Am I correct or not? You find that value, you put that value. But if you see at a CRO, no oscillation. Why? You are calculating correctly. You got that same value of capacitor there. If you connect it, it is not oscillating. Why? Huh? Oh, no, unstable maybe. Maybe unstable, maybe stable. We do not know. No problem. Why it is not oscillating? You calculated correctly. You calculate no wrong in your calculation, but it is not oscillating. Why? Why? You calculated correctly, no? Because you put 3 phase shifts here, 60, 60, 60. The components that you are using has how much tolerance? 10% tolerance. You are getting 1 kilo ohm means it may be 900 ohm to 1100 ohm. It is not correct. 10% tolerance. Sometimes 5% tolerance means it varies from 950 to 1050. So it has tolerance. That's why even if you put correct value, it is not correct because it has some tolerance. That's why you will be given one part. You will adjust the part. When you adjust that part, this oscillation comes. Am I correct or not? Because the poles should be exactly on the j omega axis. In the lab, what you are doing is, maybe here means you said unstable, you know. Why the answer is not correct means sometimes here means no sustained oscillation. It is before that j omega axis means no sustained oscillation. Initially, small oscillation you might have seen, after that it settled. If it is here means it goes to unstable. Either it goes to cutoff or saturation. Here it works as amplifier. In this part, if the pole is in the left hand side, it works as amplifier. If the pole is on the right hand side, it works as either cutoff or saturation. If exactly on the j omega axis, then only it will exhibit oscillation. So in the lab, you are adjusting the pole so that it will be on the j omega axis. Both subjects are same. You are reading different way. Both are same. There you are saying that closed loop phase shift must be 360. Total loop gain must be unity. Bargusan criterion. Am I correct? Or? Bargusan criterion. The same here. But here we are studying in different dimension. So if it satisfies the Bargusan criterion, that is for a particular value of k, it exhibits sustained oscillation. That is k max. Here we should not give k max. If you give k max, you cannot settle. Always it will oscillate. The process always will oscillate. It should settle. That's why k max is the maximum value that can be given. So for safety, it should be far less than k max. It should be far less than k max. A factor of safety is required because for resistance, you have tolerance. For capacitor, you have tolerance. For every mathematical model, there is a tolerance. You obtain this process, you are getting some model and you obtain a tuning parameter, it may be wrong. That's why we should far away from the oscillation mode. Far away from the oscillation mode. If you know K max, you can use only 50% of the gain so that you are safely away from unstable. That is called relative gain. Relatively, I am 50% away from unstable. Are you able to follow? Suppose this beam, here, this beam, actually this much size beam is not at all required. For one day use, suppose this building is used only for one day means this much is not required. 1/6 of this is sufficient. How much? For this much load, 1/6 of this is sufficient. But they are putting 6 times higher. Why? Factor of safety. Factor of safety. So the building is designed for 6 times safer than required. Because if any earthquake comes, it should withstand. That's why the buildings are designed for 6 times higher than required. You understand this? Theory, civil students will calculate what is the required amount of steel. They will calculate and they will multiply by 6. That's why if it is constructed by mason, the building is strong. Because how much it is higher? 6 times. Any small error will not affect. You understand this? So here, our controller gain must be 50% less than K max. Or the gain margin must be 2. Have you studied gain margin, phase margin? In control system, this is the meaning. Gain margin 2 means, linear scale 2 means, you are 50% away from the unstable. If you multiply the gain by 2, it becomes unstable. That is the meaning. Gain margin 2 means, if you multiply the K by 2, it becomes unstable. In the verge of instability, not unstable, in the verge of instability, it means always oscillation. Always oscillation. So, we have to find that point. How to find that point? That is K max. If you find K max, we can find the tuning parameters. That is another formula. In the previous case, in the level process, how we find Kc? Kc equal to time constant Tp divided by Kp multiplied by Td. Am I correct or not? Multiplied by 0.9 Kc. Ti equal to what? Ti equal to 3.33 times Td. Am I correct or not? 3.33 times Td. Here, K max, if you know, you can find Kc. Kc equal to 0.6 times K max. 0.45 times, sorry. 0.6 is for PID controller. This is 0.45 times K max. Only 45% is used to gain. So Ti equal to Tu divided by 1.2. Tu means it is oscillating, you know. It is oscillating. Find the period of oscillation. For one oscillation, how much time it takes? That is called Tu. That is called Tu. If you know Tu, divide by 1.2, that is Ti. This is found by Ziegler-Nichols. Ziegler-Nichols. Two scientists found this. Ziegler, one person named Ziegler, another person named Nichols. That's why it is called ZN formula. ZN thumb rule. Those days, he found in 1949. When they found the formula, when 1949. That time, no electricity. They will use this 3 to 15 psi signal will be used to transfer measurement. If they measure 100% measurement means they will send 15 psi. 0% measurement means they will send 3 psi. 50% means 9 psi. That signal used those days. That time, the PID controller can be tuned by using these two formula. They gave the thumb rule, this formula and this formula they found. No one accept that. Like if the earth is round, they said, what happens to them? They murdered, no? Like that, they didn't accept. But nowadays, everyone is using this formula. Everyone is using this formula. But Indians are not like that. Indians know 1,000 years back, earth is round. That's why they wrote Panchangam 1,000 years back. They know the movement of earth. How it works and all they know. It means that 23.5 degree inclination they know. They know sun is in the center. If you go to temple, 1,000 years back it is constructed. But where they put the sun? In the middle. They know all planets are rotating the sun. They know 1,000 years back. But in Europe, anyhow, we are far, far intelligent than anyone in the world. That's what I am telling. Say, Ziegler-Nichols found that formula. That is still used here. Thumb rule. It is thumb rule. So it is used by considering the gain margin, phase margin. Considering gain margin, phase margin. K-max we have to find. How to find K-max in this experimental setup? That we will see now. For that, this controller, we have to put the controller in closed loop initially. Put the controller in closed loop. Give some set point. Put the controller in closed loop. Give minimum gain. Give minimum gain. Because it is not K-max. Give minimum gain. It means give maximum PB. What is the relation between PB and KC? PB equal to, already we have seen, PB equal to 100 by KC. Or KC equal to 100 divided by PB. We are going to enter in terms of PB means inversely proportional. KC infinity means PB 0. KC infinity means PB 0. KC infinity means PB 0. So for maximum gain, you have to enter PB equal to 0. So you can enter any value. For minimum value means you enter 100, 200, 300 like that. If you enter 100 means PB equal to 100 means KC equal to what? 1 unity gain. So small gain, enter 400, 100 by 4, 1 by 4, 0.25 gain. Enter and put P only controller. Because we have to find, what we are finding? K-max. At what time it exhibits sustained oscillation we have to find. That's why put P only controller. Don't use I mode. Only P mode. Put P only controller here. Here put P only controller. P only controller. It means proportional controller you put. Gradually increase the gain. It means what? Gradually decrease PB. At one point, it exhibit oscillation. It will exhibit sustained oscillation. Means amplitude is constant. It exhibits oscillation. Note down that K-max. Find the period of oscillation. Find the period of oscillation. That is called TU. The value at which it exhibits sustained oscillation is K-max. You got K-max. You got TU. You can find the formula. You can find the formula. That's all. Tuning is over. What is the formula? Already I told you that KC equal to 0.45 K-max. TI equal to TU divided by 1.2. Now, how to find TU we have to find. You can find K-max just in the controller. You are decreasing PB. You are decreasing PB. At one point, it exhibits sustained oscillation. That is the required PB. That is PB min. Kc means we have to tell max. PB means min, minimum. PB min you will get that you have to divide by 0.45. If you multiply Kc max by 0.45 means PB means you have to divide by 0.45. So you got PB min, you got PB, required PB equal to PB min divided by 0.45. I got PB. How to find TI? TI equal to TU divided by 1.2. How to find TU? For that, the flow rate is going through this. The DPT measures flow rate in terms of 4 to 20 milliamps. Here, have you studied rotameter? Suppose a rotameter is here. Let us assume that one rotameter is here. This is the rotameter. Rotameter means one bob will be there. One bob will be there. Depends upon the flow rate, this bob will be there. If it exhibits sustained oscillation, flow rate is increasing, decreasing, decreasing means what will happen to the bob? It goes up and down. Goes up, again come down. Again goes up, then come down. But it should go to the particular mark and come down to particular mark. Then only it is sustained oscillation. Otherwise, if the oscillation is like this, let us assume, it means future it will settle. It is not Kc max, less than Kc max. Another one is, it goes like this. Go on increasing, but it cannot go beyond 100%. Goes to maximum, come to minimum, but if it is greater than K max, this problem will come. This is called, can be found by, it goes up and stays there for some time because it cannot go beyond 100%, you know. That's why it stays there for some time, then come down. And come down and stays there for some time and goes up. It means you whatever value you gave is greater than K max. So it will go up and immediately it should come down. That is called for value for which it exhibits sustained oscillation is called K max. Or PB min. You got PB min. TU, how it can be found? It goes up and down. It means it exhibits sustained oscillation. So measure the time. Stop clock will be given. You can find the time. If you measure for one time, it will be error. In a physics experiment and all, what you will do? In the pendulum, they will measure time for 50 oscillations or 20 oscillations. You will be asked to find. Then you divide by the 20, you will get the average value. So error free. Like that, this bob goes up and down 10 times for that measure the time. Divide by 10, you will get for one oscillation, TU you will get. Now you got TU and K PB min, you can find the tuning parameters. You understand the point? Now I will tell you, this is the experimental setup. I will tell you how to do the experiment. The experimental setup is given. VFD means what? A variable frequency drive. What it will give? Depends upon 420 milliamps. Its frequency varies. Based on that, the pump speed will be there so that no power loss. And DPT measures the flow rate, actual flow rate. It compares with the set point and gives errors. Error is given to the controller. Based on that error, the controller gives output M 420 milliamps. To do this experiment, we have to put the controller in auto mode directly. Because since it is the fast process, directly put the controller in auto mode, give some set point, give minimum controller gain or PB maximum, gradually decrease the PB. At one point, it will exhibit sustained oscillation like that. It means in the rotameter, the bob will go up and down for constant amplitude. Note down, this phenomena is called limit cycle. Now I remember the name. Limit cycle means it goes up and stays there, then come back. If you give greater than K max, limit cycle, it should not be limit cycle. So you gradually decrease the gain. At one point, it exhibits sustained oscillation. Find PB min and TU, ultimate period. U means ultimate. T max or TU, ultimate period you will get. Divide by 1.2, you will get TI. So enter those tuning parameters, and then if you vary the set point, the flow rate will be automatically fixed by the controller. The flow rate will be fixed by the controller. How to give disturbance? We have to do two experiments, one is servo, another one regulatory. Servo means you can change the set point from 50 to 55. You will get servo response. How looks like? The servo response is looking like this. Servo response for flow process is looking like this. Initially it is at 50%, you change it to 55%, set point is changed. That's why it goes up and oscillates and settles. This is servo response. Servo. Regulatory response means here one tap will be there, hand valve will be there. It is here. Actually, it is here. Before that rotameter, one valve is there. You slightly close that. Actually, you are introducing some resistance in the tube. That's why flow rate will decrease. Or if you open, resistance will decrease. That's why flow rate will increase. So you are introducing the load here, disturbance here. If you introduce that disturbance here, what will happen? Suppose you are opening more means flow rate will increase 50% initially. It increases. That's why controller takes necessary action and controls again to 50%. Again, since it is a PI controller, it will be settled. You can check for P controller whether it works or not here. If you deliberately put P only controller and give some set point, definitely now it will settle. Suppose I am in a servo response, it is initially at 50%, let us assume. You are giving 55 means it will go up and settle at some 54. Typically, I am telling, maybe it may not be correct. Experimentally, it will settle somewhere before 55. It never settle at 55. P only means this is P only. You can check in the flow process because it will settle quickly. That's why you can do that experiment. In level, you cannot do such experiments. You can do, you need a long time, but you are provided with only 3 hours. That's why you cannot do. Here you can check P only. If you put, there will be a steady state error. This is called steady state error. You might have studied steady state error in control system. Steady state error will be there. If you disturb, suppose I am disturbing the process with the P only controller means, if I disturb, initially it is at 50%, say 50%. This is cross variable. Initially it is at 50%. At this point I disturbed, it goes out and oscillates and settle like this. It may settle at somewhere 52%. Steady state error will be there. If P only controller, if you use PI controller, there won't be any steady state error. Have you understand this point? This is your second experiment. The third experiment is modeling, tuning, and closed loop control of soft process. Modeling, tuning, and closed loop control of soft process. It means simulation experiment that you have to do in the MATLAB. Here, if the order of the process increases, you will get more dead time. If I draw the response of first order process, first step response to a first order process. If you draw the step response, step input, if you give, the response will be looking like this. Am I correct or not? First order response. Second order, what is the difference between first order and second order? Here, you can notice that here the angle is 90 degree. For second order, it is not 90 degree. That is the difference. Otherwise, both are looking same. As order increases, suppose order is fourth order means it will be like this. That's why in the level process, you got S curve. This is called S curve, reaction. As order increases, you will get S curve. The dead time will come into picture. Initially, there is no response for some time as order increases. To understand how the delay comes in, you can understand from practical example means, let us assume that each vehicle, car or bike is first order, let us assume. Minimum order is first order. No zero order in the world. Zero order means analytical equation. No system in the world is zero order. Zero order means immediate output. It's not possible. It's not possible. If you get something means for that you can react after some time only. Millisecond or microsecond delay definitely minimum required. Vehicle, all vehicles are first order. Let us assume. If you are in the signal, some 4 or 5 vehicles are there before you, the signal changes, all vehicles simultaneously moves. No, you have to wait for some time. So as order increases, there will be delay in the response. Suppose 4th vehicle means for that vehicle in that system, it is 4th order because some 3 first order systems are cascaded to that, added to that. That's why it is 4th order system. First vehicle only first order, second vehicle second order, 4th vehicle 4th order. So there will be a delay that you can understand. That's why you will get a delay here, TD you will get. The time constant is from here to here, that is called 63%, 63.2% is the time constant, TP. Gain, you know how to calculate. That's why to get reaction curve, we are going to simulate a 4th order process. 4th order process, let us take this way, 1 by s plus 1 to the power 4. 1 by s plus 1 to the power 4. That you have to simulate in the MATLAB. So if you expand this, what you will get? S power 4 plus 4 s square plus s cube plus 6s square plus 4s plus 1. So how to get this? 1, 1, 1, 1, 2, 1. This is 0 order, first order, second order. Third order means 1, 3, 3, 1. Coefficients of the terms. Fourth order means 1, 4, 6, 4, 1. You have to use this triangle to find the coefficients. So fourth order means this is the coefficients. Coefficients are 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. This is fourth order transfer function. Therefore, the fourth order transfer function is 1 upon this. This is for this we have to do closed loop control. We have to do closed loop control. So to do closed loop control, we have to find Kc Ti. Here, since it is simulation, it is fast only. Whether it is 4th order, 10th order, 100th order, same time it will take. Simulation only. Mathematically, we are calculating. Computer calculates mathematically output. That's why all are fast. That's why we can tune both ways, reaction curve method as well as closed loop method, sustained oscillation method. So we have to find in both methods Kc and Ti, we have to compare the result. That's all. Kc and Ti we have to calculate. First thing what we have to do, first thing is we have to take the 4th order process. 1 by s plus 1 to the power 4. Reaction curve method means give you a step input. You will get the reaction curve. You will get the reaction curve. Find Kp, find Kp, Tp, Td. Dead time you have to find. This is dead time. Time constant you have to find Tp. Then gain you have to find Kp. If you know all these three values, you can find the tuning parameters, that is Kc equal to 0.45 for P only controller. For P only controller, then PI controller, PID controller. All 3 controllers you do so that you can, what is the response you can see. For P only controller means only in Kc. For PI controller, you have to find Kc and Ti. For PID controller, you have to find Kc, Ti, Td. For P only controller, Kc equal to Tp divided by Td multiplied by Kp.
So we have to find that way. TP divided by TD multiplied by KP. No TI, no TD, because only P only controller. PI controller means 0.9 times TP divided by TD KP. PI controller means 0.45 and 0.9%. For TI, 3.33 times TD. For PID controller, this is how much? 1.2 times. 1.2 times TP divided by TD KP. This is equal to 2 times TD. This is 0.5 times TD. That's all. So we have to find the reaction curve, find TD, TP, KP, and substitute, you will get the tuning parameters. By simulation, you have to find the servo and regulatory response using P only controller. Find servo and regulatory response by using PI controller. Find servo and regulatory response using PID controller. You will get 6 responses you will get. Then tune by using closed loop method. So for that, what you have to do? You have to take the process 1 by s plus 1 to the power 4. Put a P only controller. Put it in closed loop. Vary Kc. It exhibits sustained oscillation. That find K max. You find TU. You got these 2 parameters so that you can find for tuning parameters. You can find tuning parameters, that is P plus I, P plus I plus D. KC, TI, TD, you have to find. This is 0.5 times K max. No TI, no TD. This is 0.45 times K max. TI equal to TU divided by 1.2. No TD, only PI controller. Here 0.6 times K max. So you get all the 3 controller parameters, you can do the simulation. That's all. Now we'll see how to do all these experiments by using MATLAB. Here also you have to get another 6 experiments. For P only controller, find servo and regulatory. For PI controller, find servo and regulatory. Compare these 2 parameters. How to compare these 2? How to check which controller is best? How to find which controller is best? For that, what we have to do? We have to do one measure. That measure is called ISE-IA. You have studied integral square error, integral absolute error. These are all parameters to measure the performance of controller. So here, if you draw the graph for error, suppose it is looking for regulatory response, it is looking like this for one controller. Another controller, it is looking like this. Which is best? First one is best. If you integrate this by taking absolute error, means positive also becomes negative, also becomes positive. If you integrate that, you will get one area under this graph, you will get absolute error if you integrate. Similarly, for this also, you will get under area under this. Which area will be higher? Second graph. Therefore, ISE-IA must be minimum for better controller. So you can analytically, you can find which one is best controller, you can find. In this way, you have to find ISE-IA. How to find all these things by simulation, that we'll see now. Simulink. Simulink is the blocks are available. Suppose you want a transfer function, means that is available as a block. You want a PID controller, means you need not write program. That is that program is put in a box and it is available as a component. You can just connect. It will be converted into program automatically inside. So that is called the Simulink. The Simulink will be very simple to do simulation. That's why we have to invoke that Simulink. So I got Simulink. So you have to get a blank model, create a model. So you'll get a blank model. So you got a blank model. If you browse that library, you will get these blocks. You have to drag and drop, that's all these modules. You need a transfer function. You need a transfer function. For that, you will get sources if you go. Continuous if you go, you will get transfer function. Here, you are having, where is the transfer function is available here. You can drag and drop, that's all. So you got transfer function. Initially, what you have to do? You have to do, you have to do reaction curve. For that, we need a step response. That's why source, if you go, you will get step input. You need step function is required. So you got step function. So you need sinks you required. So scope, to see the response, you need scope. So you need a scope, that's all. To get reaction curve, you need a transfer function, step function, and scope. Scope is to see the response, that's all. So you have to connect this and this. You have to connect this and this, that's all. So you have to enter the correct parameters. Here, the transfer function, if you see that, here it is a first order transfer function. Time constant is 1. Numerator is polynomial is 1. It means k equal to 1. Denominator 1 means s plus 1. S plus 1. But we have to enter fourth order. So what we have to enter is 1 s power 4, then 4s cube, 4s cube, 6 s square, then 4s, then 1. Now we entered fourth order. That's all. So it becomes fourth order. Yes, we got that fourth order. Fourth order response we got. So here, step input, we have to give correct parameters. It is not correct. Here, the step time is 1, but you need at 0 time. You need a step input. Final value is 1. Unity step input you are giving. That's why it is okay. So scope is you have to see the response. That's all. Now we have to simulate. Let us simulate for 10 seconds. If you simulate, it won't give complete. It won't settle in 1 second. Let us check. Yes. It is not yet settled. The response we got, step response we got, but it is not yet settled. That's why we have to simulate at least for some 20 seconds. 20 seconds. We got the response. Reaction curve we got. You find dead time. You draw a slope where the slope is maximum. It will cut the x-axis at this point. Find the time at which it cut the x-axis. So you will get the dead time. Time taken to find reach 63.2%. You draw a vertical line at 63.2%. You will get time constant. Gain is unity. Where it is settled? Settled at 1. What is the input you gave? 1. So the output is 1. Input also 1. That's why gain is unity. Therefore, Kc equal to 1. So we got Kc equal to 1. Let us go here. We got, I know the values. That's why I'll find the tuning parameters by reaction curve method. Kc equal to what? For P only controller. Kc equal to what? Tp plus Td equal to total time taken to reach 63.2% is 4.35. Here, dead time is 1.35. Td equal to 1.35. From the graph you can get. Therefore, Tp equal to 3 seconds. Kp equal to what? Kp equal to 1. So now we can find the tuning parameters. What is that? Kc equal to what? Find Tp equal to 3 divided by 1.35 multiplied by 1. How much? This is for P only controller. Huh? 2.22. Okay. For PI controller, Kc equal to 0.9 times 2.22. How much? How much? 1 point? How much? 2. Exactly 2. Okay. 2. Okay. Kc equal to 2. Ta equal to what? Ta equal to 3.33 times 1.35. Equal to how much? 4.49. Okay. For PID controller, tuning parameters are Kc equal to 1.2 times 2.22. How much? 2.66. Okay. Ta equal to 2 times 1 point, dead time is 1.35, therefore 2.7. Ta equal to 2.7. Td equal to what? Td equal to 0.675. 675. Am I correct? Check. Check. Correct? How much? 1.35 divided by 2. 1.35 divided by 2. 0.675. Okay. We got the tuning parameters. Now we can simulate. So we have to simulate this and we'll go there. I got all this PID. In continuous only PID is available. This transfer function also available in continuous. Step is available in the source. This is available in mass. Sum, this block is called sum. This is available in the sync. These two are available in the math. So you can search by name and you can get the blocks. Now we got all blocks. Now we have to give step input. So we have to get the step input also. This is sources. Step input is required. Yes, we got step. This is display. These two are display. To display IAC, IAE, I got these two. So PID block we got. So connect this. So we have to calculate error. Error, if you know, you can calculate two things. One is ISE, IAE. I will tell what is that. Then I will come here. Okay, after finish, I will tell that. We have to find the ISE, IAE. This is to get ISE. Square of that error you will get, and Here you will get absolute error. IAE. So we are taking error and give it to square module. So you will get integral of square of that error you will get. Here integral of absolute error you will get. So everything is given. Now we have to check the parameters of step input. So it should be given at 0. So we are giving 0. That's all. Unit step input. And the PID controller for P only controller. What is the value we got for P only controller? What value you got? 2.2. Am I correct? 2.22. 2.22. And here you have to see the formula. PID. Everything is in the numerator. That's why I we can substitute 0. Sometimes if it is Kc by Ti means you should not enter Ti equal to 0. So here we can enter 0 because it is I only. D also we can enter 0. That's all. So we entered P only controller. Now we can simulate for servo response. If you give step input, here in simulation, 0 is the nominal value. 0 is the nominal value. Wherever it is settled, that is nominal value. If 50% already it is settled at 50% means 50% will be taken as 0. You understand this? So like that you have to do simulation. So run for some 50 seconds. Run for 50 seconds. Here I didn't enter the correct parameters. We have to do negative feedback. I gave positive feedback. That's why unstable. So we have to give minus sign. I forgot to give negative. Now it is negative feedback. So now we have to simulate. We got ISE, IAE. This is IAE 0.3. ISE is 0.09. We have to see the response. Yes, we got. What is the set point? Set point is 1. Where it is settled? Settled at the points between 0.6 and 0.8. Are you able to follow? It is settled between 0.6 and 0.8. What is the set point? 1. What is the controller we are using? P only controller. If you use PI controller, then only the steady state error will be removed of controller. Now we will do the PI controller and see the response. Here PI controller means 0.9 times. Am I correct or not? Multiplied by 0.9. What is I mode? So we have to enter the tuning parameters for PI controller. For Kc equal to 2.22 multiplied by 0.9. Kc equal to what? 0.9 times 2.2. 0.9. 0.9 multiplied by 0.9 multiplied by 2. You will get. Yes, we got. Where it is settled? Settled at 1. Settled at 1. No steady state error. No steady state error. You got servo response. Here, you note down the ISE IAE. We'll change it to PID controller, then we will check. No error. But you check the ISE IAE. See the ISE IAE. If you use PID controller, PID controller, it must be multiplied by 1.2 multiplied by 1.2. Am I correct or not? Small oscillation is more. But IAE is more means it considers all errors equally. Even small errors it doesn't permit. It takes into account. That's why we got large value of IAE, but smaller value of IAC means smaller errors persist for long time. Smaller error persist for long time. That is the meaning. Now we'll use by using closed loop method. For closed loop method, what we have to do is we have to make this P only controller. First step is we have to put this in closed loop. First step is we have to put this in closed loop. We put already in closed loop and we don't want any I mode. That's why multiplied by 0. We don't want any derivative mode. Multiplied by 0. That also multiplied by 0. Only derivative mode. Only proportional only mode. Let us give gain smaller value. We will gradually increase smaller value. So let us give initially 1 or let us multiply this by 50% of this value we will give. 2.22 multiplied by 0.25. 0.25. Let us start from here. 0.25. Let us give 2 initially and multiplied by 0.25. Apply. Small gain I gave. I am seeing the response. Steady state error is there. Where it is settled 0.35 only. What is the set point? 1, but it is settled at 0.35. If I increase the gain, what happens to the response you see? If I increase the gain, this is the advantage of simulation. If you do all this simulation, we can understand many things. If I make gain more, if I increase the gain, 2 multiplied by 0.25, how much? 0.5. Am I correct or not? Now I am making this 0.5. 2 multiplied by 0.5, how much? 1. I am giving 1. Now what is the response? What is the response? You see? Now, where it is settled? Earlier it is settled at 0.35. If we increase gain, it is settled at 0.5. But still steady state error is there. It is not yet settled at 1. If I increase to, if I increase the gain to further, 1.5 times. So I am increasing the gain 1.5 times 2. 1.5 times. 0.5 times now. 1.5 times. 1.5 times means what? How much? 2 multiplied 1.5, how much? 3. No? Okay. Now you see the response. Proportional only controller. Definitely steady state error will be there. Where it is settled? Settled at 0.7. Steady state error is decreasing. As gain increases, steady state error decreasing, but more oscillation. More oscillation. Steady state error decreases. That is the only advantage. Now let us starts oscillating means gradually increase the gain, starts oscillating, you know. For 0.25, no oscillation. 0.5 slight oscillation. Now 3 gain is increased from 0.25 means 0.5, 1, 3. Now let us give 5. What happens? Let us give 5. Let us multiply it by 3. 6 I am giving. Deliberately I am giving 6 and check the response. Unstable. It becomes unstable. So it must be less than 6. K max must be less than 6. I know the value of K max. That's why deliberately I skipped that value. If I give multiplied by 2. Multiplied by 2. 4. Now, how much gain I gave? 4. See the response. Sustained oscillation. By using Routh criterion, you can find the value. For that fourth order process, if you find a Routh criterion, K max equal to 4, you will get. So sustained oscillation, you got for K max. For K max, you got the sustained oscillation. Now we have to find the TU. So for that, enlarge this and find K TU. TU equal to how much? Where it matches the scale. Here almost it matches the scale. Almost here it matches the scale. Here 45. Here it is 39. 6 almost. 6, you know. TU equal to 6. 6 or 5? 6. 6. So here, there you can amplify and see. Here also you can amplify and how to amplify. Here you can amplify this and see. This you have to double. You can amplify and see like this. Time axis has to be amplified. You amplify and you can see more coordinates so that you can find correct value. I know 6, I know. That's why I'm telling that 6. So you can see here, and it is 6. That's why now we know these two values. That's why we can find the tuning parameters now. What is tuning parameters for these two values? We got K max equal to, we got K max equal to 4 and TU equal to 6, we got 6 seconds. From this, we can find the tuning parameters. For KC, it is 0.5 times K max. Therefore, KC equal to, for P only controller, for P only controller, for PI controller, for PID controller, KC is 2.5 times. No TI, no TD. TI, TD. For PI controller, it is 0.45 times. 0.45 times means 1.8. 1.8. This is TU by 1.2. 6 divided by 1.2. How much? How much? 5. So, no TD. For PID controller, how much you are getting? This is here 0.4, it's 0.6 times. 2.4 you will get. What you will get? TU by 2 means here you will get 3. Here TU by 8, how much? 0.75. That's all. Now we'll see. This is the best tuning parameter using Ziegler-Nichols. Why? There, from the reaction curve, we approximated TD, we approximated TP. This is not exact value. But here, by simulation, we got the exact sustained oscillation. That's why by Ziegler-Nichols method, it must be 1.2. But reaction curve method, how much you got? 2.2 you got. Here you got 2. Here you got 2.2. Here, what is that? 2.22 multiplied by 0.9 is 2. But here, what you got? 1.8 only. Nearest value only you are getting in reaction curve method. There is no wrong in it. That's why it is retunable. If you get more oscillation, you can reduce gain. You can increase TI. You can reduce TD. Like that, you can do adjustments. It is not a fixed rule. That you can modify after seeing the response. This is only thumb rule. So now let us do simulation for all these parameters.
2, 1.85, 2.43 and 0.75. Before that, what is integral of error? Integral of E dt means you are finding error, absolute error. So error like this means you are making the graph like this and finding integral. That is absolute error. Integral of square error means integral of E square dt means you are squaring this value. If you divided by 1.35 multiplied by 1.2. How much? 2.2. 2.67. Okay. Here 2.67 divided by 2.67 divided by TI equal to how much? 1.35 multiplied by 3.33 multiplied by 3.33. Yes, I got. Here 2.67 multiplied by TD equal to how much? Not 33 for this divided by what is that? 8, you know. T divided by 2. You know? Okay. Here TD KC multiplied by TD. TD equal to how much? Multiplied by 0.5. 0.0675. Okay. 0.675. 675. Okay. These are the tuning parameters for PID controller. Now let us run. Which gives better response? Reaction curve is better because gain is more. Reaction curve is better because gain is more. If you increase slightly Kc, response become better, but at the cost of oscillation. Another thing is threat to stability. Threat to stability. We are going close to j omega axis. That's why threat to stability. These are the two reasons, but response will be better. These are all up to us to find tuning parameters. One will be better anyhow. If Kc is more, because here Kc is higher value, 2.6, here only 2.2. That's why reaction curve gives better response than sustained oscillation method, but at the cost of more oscillations and threat to stability. That's all. So with that, but you have to do for P and PI in the lab, but I did only for PID. Control valve is final control element used to control flow rate. Wherever you want to control the flow rate of liquid, you need a control valve. Control valve is yes. Yes.
This is the control valve. This is the stem. This is the wall plug. Here, this is the flexible member. This one blue is the flexible member. Flexible member. Diaphragm. If air inlet is given here, the 3 to 15 psi we have seen, that 3 to 15 psi is applied here. When 3 psi is, this is the position. The valve plug will be like this. The liquid will enter through this and it will go through this, and leave through this. Against gravity, it will flow. When 3 psi is applied, when 15 psi is applied, the valve will be completely closed. Here, the plug position will be like this. Completely closed. This is completely closed. This is completely closed. Yes. Completely closed. If 3 psi is given, it will be like this. Its position will be like this, because 3 psi means it regained to initial position. If you apply 15 psi, higher pressure, it will come down and completely closed. So it requires air to close. That's why this types of valve is called air to close. Air to close valve. For 3 psi, 100% open. For 15 psi, 100% closed. For 3 psi, completely closed. 3 psi. This is the position for 3 psi. This is the position for 15 psi. Position for 15 psi. This is air to open. There are two types of valves. One is air to close, another one is air to open. The difference is if you apply the inlet air in the top side, it is air to close. So here it will be like this. Same will be here. The air will be applied here. Air inlet. So by looking at the valve, if air inlet is on the top side means air to close. Air inlet is in the bottom means air to open. So this, so the valve position, valve plug position will determine whether it is completely open or completely closed. Here, for 3 psi, it is completely open. For 15 psi, it is completely closed. Therefore, air is required to close. That's why this valve is called air to close. Here, for 3 psi, it is completely closed. So we have to lift this plug up so that it will be open. Air is required to open. That's why air to open type. So there are two types. Basically two types, air to open, air to close. What is the need of the spring?
Suppose we are applying 15 psi. It is completely closed. Am I correct or not? I am withdrawing the pressure suddenly. Where it has to go, it should completely open, you know. That's why the spring will open completely. So the pressure will work against spring. The pressure will work against spring. That's why if you remove that pressure, automatically it regains to original position. That's why the spring is spring loaded. The stem is loaded with the spring. That is, there are initially two types. One is called air to close, another one is called air to open. Another difference is there. That difference is one is called a linear valve. Linear valve. That linear valve means its behavior will be linear. Its behavior will be linear. If you plot between valve opening, how it varies 3 to 15 psi, or we can say that 0 to 100%. 0 to 100%. We can say that 0 to 100%. 50% means 9 psi. What is the middle value? Middle value is 9 psi. 9 psi means middle value, 50% open. So here also 0 to 100%. Linear means for opening, this is the x-axis is open. 0 to 100% opening, the flow rate is varying linearly like this. 0 to 100%. Flow rate also varies from 0 to 100%. Then it is called linear valve. Provided the pressure drop across the valve is constant. If between this and A, this end is A, this end is B. Inlet is B, outlet is A. If pressure across A and B is constant, then the linear valve will give linear flow rate. Linear flow rate. If opening is 50%, flow rate also will be 50%. If opening is 100%, flow rate also 100%. Flow rate opening is 0%, flow rate 0%. So that it behaves like linear. Another valve is there. Its behavior will be equal percentage. 100%. Flow rate will be 100%. For 50% opening, maybe flow rate may be 25%, around 25%. So it is not uniform, non-linear behavior. This is equal percentage valve. Equal percentage valve. How this difference came into picture means depends upon the dimension of the plug dimension. That is mechanical subject. How the plug dimension is there, accordingly, the flow rate will vary like this. So, if the plug is designed in such a way that it gives linear flow rate, the plug is designed such a way that it gives non-linear flow rate. For 50% gives only 25, but after that it suddenly increases. So after 50% opening, it increases very fast. On 100% open, it goes to 100% flow rate. So this is flow rate. This is flow rate. Flow rate is in y-axis. Flow rate is in y-axis. Opening is in the x-axis. Opening is in x-axis. 0 to 100% opening. 0 to 100% open. Another control valve, another design in the plug shape is there. That is called quick opening. Quick opening. Quick opening. It will be like this. For 50% opening, it will give around 75% flow rate. For 100% opening, it gives 100% flow rate. And for 25%, it gives almost 50% flow rate. This is quickly opens. These are all depends upon the shape of the plug, valve plug. Provided pressure drop across the valve is constant. This is possible only when pressure drop across the valve is constant. This characteristic is called inherent characteristics. Inherent characteristics. We call the valve by inherent characteristics. If we keep the pressure drop across the valve constant, it behaves like this. If the relation between opening and flow rate is linear, then it is called linear valve, provided the pressure drop across the valve is constant. If it behaves for 50%, it opens, so it flow rate increases only up to 25% around. I'm not, this is typical value, not exactly. It is not 50%, less than 50% means it is equal percentage. The flow rate for 50% open, flow rate is above 50% means quick opening valve. This is called quick opening. Quick opening. Quick opening valve, equal percentage valve, linear. There are three types of valves are there. So, linear valve may be air to open, air to close. Equal percentage valve also can be air to open, air to close. There is no distinction. We can made either air to open or air to close. Similarly, quick opening also can be air to open or air to close. So six way we can classify. Each one can be air to open or air to close. So you can understand from the where we are giving air inlet, from that you can understand that whether it is air to open or air to close. That you can understand. If it is in the bottom, air to open. If it is in the top, air to close. That's all. Here, if the pressure drop is constant, the pressure drop across the valve is constant. This is the pipeline connected to valve. Connected to the valve. This is the valve symbol. I am using symbol now. So here, some constant pressure is here. Constant pressure. Because here one overhead tank is there. The tank is full always. The tank level varies. Pressure will vary. No. That's why let us assume that tank is always full. Tank is always full. That's why the pressure at this point at A is constant. Pressure at B is constant, atmospheric pressure. So pressure between A and B is constant because tank is always full. Point B is at atmospheric pressure constant. But what is the pressure just before valve is not constant? Because the pressure drop in the line has some resistance. Line has like a copper wire, even it may be a copper wire, it has resistance. There will be a potential drop. That's why at peak hours, we may get less voltage. The line drop because of large current. Line drop is function of current, not voltage. So I multiplied by R, large current, that's why large voltage drop. That's why we are getting low voltage at peak hours. Like that, here also the line will drop the pressure. So this line drops the pressure, it is function of flow rate, like current. Function of flow rate, drop in the line is function of flow rate. That's why if you open the valve fully, flow rate will be maximum. That's why drop will be more in the line. If you open 25%, flow rate is very minimum. That's why drop in the line will be minimum. That's why if you see the pressure drop across the valve, pressure drop across the valve is not constant. But what we have seen is, if pressure drop across the valve is constant, then only it will be linear. If pressure drop across the valve is constant, then only it will be equal percentage. The shape is called equal percentage. The pressure drop across the valve is constant, then only it will be quick opening. Pressure varies, what will happen? That we have to see. If pressure drop is more, for more flow rate means the pressure drop across the valve, pressure across the valve will be minimum. Am I correct or not? For maximum flow rate, pressure across the valve will be minimum.
For minimum flow rate, pressure across the valve will be maximum. Am I correct or not? When the flow rate is minimum, line drop is minimum because flow rate is very small. That's why pressure drop across the valve will be large. When the flow rate is maximum, the line drop is more. That's why pressure drop across the valve is minimum. That's why it is not uniform. The pressure drop across the valve is varying. If we allow to vary the pressure drop, what is the characteristics? How the characteristic will vary? The linear valve will be looking like this. The linear valve will be looking like this. Linear valve will be looking like this. This characteristic is if pressure drop constant. This characteristic is if pressure drop varies as function of flow rate. Flow rate as function of flow rate. If you allow to vary the pressure drop, it will be like this. Here, equal percentage, it will be like this. This is pressure drop varies. Pressure drop varies. Pressure drop constant. Here, it becomes more quick opening. This is pressure drop varies. Here, pressure drop across valve. Pressure drop across valve constant. So what happens to the characteristics? If it is linear valve, it is not linear, no more. If pressure drop across the valve is not constant. If it is equal percentage, it becomes linear. It becomes linear. If it is quick opening, it becomes more quick opening. This is when pressure drop is constant, means this is the inherent characteristics. That is called inherent characteristics. This is called inherent characteristics. Inherent characteristics. This is called installed characteristics. Installed characteristics. If you install in a line, it becomes like this. That's why it is called installed characteristics. But if pressure drop across the valve is constant, then it is linear valve. That's why it is called inherent characteristics. Inherent nature is linear. But under installed condition, it is not linear. It is quick opening. If we take the equal percentage, inherent characteristics is equal percentage. Installed characteristics is linear. Installed characteristics is linear. Quick opening, inherent characteristics is quick opening. Installed characteristics is more quick opening. More quick opening. That is the difference. So you have to get all these 6 characteristics in the lab. How to get the inherent characteristics? We have to get the inherent characteristics. When the pressure drop across the valve will be minimum. Suppose I am having one deliberate hand valve is here. I am putting a hand valve here. Deliberate hand valve is here. The flow rate is small. That's why pressure drop across the valve will be maximum. Always here 0. At point B, always 0. Open atmosphere. Here, the pressure will be higher at low, small flow rate, say 10% opening. But I am closing this. I am closing this. If I close that, I am introducing some resistance. Am I correct or not? In the line, I am introducing more resistance. That's why pressure will drop here. More pressure drop will happens here. Pressure drop will occur. Pressure drop will occur here. That's why pressure across the valve will be reduced further. Now, when the pressure drop across the valve will be minimum. If it is not there, let us assume that it is not there. When the pressure drop across the valve will be minimum. Pressure drop across the valve will be minimum when for 100% flow rate. Am I correct or not? The flow rate is maximum, line drop will be maximum. Here itself it will drop. Here itself, everywhere the pressure drop is there. That's why here you will get minimum pressure. Here you will get minimum pressure at 100% flow rate. So, if I put a hand valve here, suppose I am opening 50%, the pressure across the valve will be higher.
by closing this hand valve, I can keep the same pressure drop across the valve. Is it possible or not? How to do that? For that, one single column manometer is there. Single column manometer is there. This is the single column manometer. Single column manometer means a tube, that's all. Tube is connected here. A tube is connected here. That's all. If you connect a tube, what will happen? The column will be filled, depends upon the pressure. What is the pressure here? Here, what is the pressure? 0. Am I correct or not? It is open to atmosphere. Other end is connected just before the valve. If pressure is more, here, this will be filled with liquid up to this much height. Suppose flow rate is 50% means it will come down here. If the flow rate is 100% means it will come down here. This is for 100%. This is for 50%. This is for 0% flow rate. If flow rate is 0% means it will be up to this tank. Up to this tank it will fill. Am I correct or not? It will fill up to the tank. Am I correct or not? Up to the tank. 0% flow rate means it will come up to this point. So depends upon the pressure drop in the line. This will vary, but for 100% it will be minimum. So how I can keep pressure drop across the valve constant is, for 100%, suppose the marking is here. So for 50% opening, it comes here. It comes here. It comes here. It comes here. Now I can close this hand valve so that I can introduce additional pressure drop so that the 50% come to this point. It will come to C. It will come to C. Am I correct or not? Are you able to follow what I am saying? If you deliberately close that hand valve, this height will decrease. This height will decrease. By doing this way, we can keep pressure drop across the valve constant for all opening. Otherwise, for 100%, it will be minimum. For 0%, it will be maximum. So, to keep constant for all, it is possible to have minimum value for all opening. It is possible. By closing this hand valve, I am introducing additional pressure drop in the line so that I can maintain always this pressure across the valve. I can do the experiment. That experiment is called inherent characteristics. What you have to do for 100% flow rate, what is the column level in the single column manometer? Single column manometer means a column tube will be, transparent tube is connected just before the valve. Just before the valve, a transparent manometer is, single column manometer is, transparent tube is connected. That is called a single column manometer. That the level in that single column will be for 100% minimum, 0% maximum. So by using this hand valve, you can adjust always the level equal to 100%. So that you are keeping the pressure drop across the valve constant. For that, what is the flow rate? How to measure flow rate? For that, here, one rotameter is fixed. One rotameter is fixed here. One rotameter is fixed. You know what is rotameter? Rotameter indicates the flow rate 0 to 30 liters per hour. Here you can notice the rotameter flow rate. So if you draw that characteristics, you are making the opening for 0%, 25%, 50%, 75%, and 100%. Or you can do for 0%, 20%, 40%, 60%, 80%, and 100%. This can be easily done because the stem is in the stem. Where is that? Here in the stem, one scale will be there. One scale is there in the stem. One scale is fitted here. Here one marking is there. Here there are 5 divisions so that you can opening can be varied in 5 different ways: 0, 20%, 40%, 60%, 100%. So you can see what is the opening. You can see here in the scale. This is the scale. Stem position scale. Stem position scale. By using that scale, you can see the opening. How to vary the opening? Here, air inlet can be varied by air regulator is given. By adjusting this, you can vary the opening. You can vary the opening. You cannot do manually. You cannot move the stem yourself. By applying the pressure, we can move the stem so that for different opening, what is the flow rate? If it is in linear valve, its characteristics will be like this. Then immediately what you can do is you can fix the rated flow rate. Suppose this linear valve is 400 liters per hour for 100% opening, means you open 100%, open the valve 100%. Here the scale, it indicates that fully open. Fully open. That time you fix by this regulating this hand valve, fix 400 liters per hour. Then allowed to vary the pressure drop across the valve. Don't adjust this hand valve after that. Allowed to vary the pressure drop across the valve and get the characteristics. This is what? Inherent characteristics. Inherent characteristics. Now you allow the pressure drop across the valve to vary. That's why you will get a characteristics like this. This is called installed characteristics. Installed characteristics. What is the maximum flow rate? 400 liters per hour. 400 liters per hour. So you got two characteristics for equal percentage. Sorry, linear valve. Then do the same thing for equal percentage. Do the same thing for quick opening. You will get characteristics like this. That's all. That's all about the experiment. So the experimental setup is available there. Here one pump pumps the water from sump to tank. It always pumps excess than required. That's why always there will be overflow. One overflow tube will be there. Always there will be an overflow. That's why tank always constant. Tank level is always constant. You are keeping the pressure drop across these 2 points, A and B, constant always. But the inherent characteristics, you have to keep pressure drop across C and B constant. C and B constant. Here it should be, for inherent characteristics, this length must be at constant pressure drop. For installed characteristics, between A and B should be constant. Between A and B, installed characteristics between A and B is constant. In industries, we can keep between A and B constant. We cannot maintain between C and B. That's why it is called installed characteristics. After installing in the system, then how it behaves, then it's called installed characteristics. So this way you have to do the experiment. Another experiment, the next experiment is here, one point I want to mention here is, we are saying that it is perfectly linear for inherent. Installed, it gives quick opening. Similarly, you can expect that this you will get. But in the case of equal percentage, for inherent characteristics, you will get like this. Like this. For installed characteristics, you are expecting that it will be linear like that. It may be like this. It may be like this. It means it moves towards linear. That depends upon the length of the tube. It is function of length of the tube, you know. It is function of length of the tube. The length from A to B. That's why here the length may not be sufficient to make linear. So the valve plug is designed for particular use. Depends upon the length of the tube. That's why you can expect that it will move up. You cannot expect a linear. That is also there. That point I want to mention. But all other cases for quick opening, it will become more quick opening. Linear becomes quick opening. Linear becomes quick opening.